My voice is audible.
Yeah, yes.
Good morning to one and all present over here. It's my immense pleasure to introduce Dr. S. Bothre. Dr. S. Bothre is Principal Scientist of Societal Electronics Group at CSIR Central Electronics Engineering Research Institute, Pilani. He has involved in design and development of intelligent instruments and a real-time control system for applications in water, low-power electric vehicle, assistive technology, automotive, and robotic industries. He is also an associate professor at Academy of Scientific and Innovative Research in New Delhi. He has 14 years of multiple disciplinary and R&D experience and also published more than 60 research papers in international and national journal conferences. He has a strong background and hands-on experience of R&D in modeling, design of electronic circuits, software implementation for automation and process control of clean water RO plant for brackish water, desalination of seawater, electronic nose system, gas sensor system for environmental monitoring. The AI controller, SMA actuator, low power electronic vehicle, assistive technology for disabled and elderly people, and robotics for societal application. We welcome you, sir, and the forum is all yours. Thank you.
Thank you so much. Am I audible?
Yes, sir. Yes, sir, you are audible, sir.
Great. Let me share my slides. Is my slide visible? Hello. Am I audible?
Sir, yes, sir. Your screen is visible.
Thank you so much for introducing me and giving me an opportunity to speak on design practice of cyber physical system and approach. This is the capacity building on cyber physical system. So this is the agenda of my speech. So we will see what is the cyber physical system. Almost all speakers have defined what is the cyber physical system. They have shared their knowledge, experiences, and developments in various applications, aviations, smart cities, smart homes, strategic sectors, healthcare sectors, automotive sectors, so on and so forth. Then design processes, modeling, design, and analysis from embedded system. What are the different blocks of the cyber physical systems, considering the embedded system techniques into consideration. Then what are the requirements, characteristics, design flow, embedded system hardware, software, evaluation and validation. And lastly, we will see a case study of cyber physical water purification and recycling system. So cyber physical system is an integration of computations and the physical process behavior is defined using cyber systems, means computing platforms, physical systems, embedded computers, networks, and monitor and control the physical processes. Usually the feedback loops where the physical processes affect the computations and vice versa. Here, the overall concept considered as you have a physical system and you have a computing system, and it is the interface integration of these two systems to derive, to call it as a cyber physical system. An example of any water purification system of a colony or any society which is producing a water purified water of 1,000 to 5,000 liters, then that purification plant is called as the or is considered a physical system, and the automation based on the computing platform is considered as the cyber system. So integration of these two techniques, these two systems, is nothing but a cyber physical system. What are the different we design any cyber physical system? There are three aspects of designing: modeling, design, and analysis. What is modeling then? Modeling is consisting of the process of gaining a deeper understanding of a system through imitation. We have to take into consideration different parameters of the physical system, and we are supposed to model that system, cyber physical system, in terms of either mathematical equations, or you can use MATLAB simulation techniques or any Python techniques to model that physical system, imitation of that physical system into the simulation platform. Models imitate the system, reflect properties of the system. Models specify what a system does. The next step is design. It is a structured creation of artifacts which provides how a system does what it does. In design, we have input, processing, and output parameters, and we have to design the cyber physical system by taking into consideration different aspects. The next step is analysis. Analysis steps plays very important role in designing of any cyber physical system. It consists of process of gaining a deeper understanding of a system through dissection. It specifies why a system does what it does. And here at the bottom side, this image is showing how these three blocks are interconnected and interdependent while designing cyber physical system. Now we will directly go into the grid system approach for design of cyber physical system. Already various speakers, they have talked about various applications, definitions of cyber physical system. Now my key focus on today's talk is on design aspects of cyber physical system. What are the things needed for designing of cyber physical system, taking into consideration embedded system? So embedded systems are information processing systems embedded into a large product. This is defined by Peter Marvin. What Lee is saying, embedded software in cyber physical system in terms of embedded software, it is a software integrated with physical processes. A technical problem in managing time and concurrency in computational systems. So Lee is CPS in terms of by taking into consideration time and concurrency of computational systems. However, Marvadel is defining embedded system or information processing systems embedded into a larger product. So he is talking in terms of hardware. Lee is talking in terms of software. So cyber physical systems are integrations of computation with physical systems or processes, is again defined by Lee. So as defined by Marvadel and Lee, So it is the integration of small computers, embedded systems, and embedded systems computers in physical environment. So what is the CPS in nutshell then? CPS, earlier we were defining control system with the help of different blocks like reference, error, controller, plant, and position. So in the era of CPS, it is defined with the help of parameters like cyber for controller and physical for plant. So integration of cyber and physics is shown over here to derive any cyber physical system. What are the different blocks needed for designing of any cyber physical system? First one is the communication technology. Second is the embedded system technology, and pervasive or ubiquitous computing. So communication technologies incorporated optical networking, network management, distributed applications, service provisions, and different platforms like DCT, Apple and ATMs. The quality of these services governs or decides how the embedded systems or computing platforms are communicating with the physical world, and physical world is communicating with the computing platform. The embedded systems technology. What are the embedded system technologies are taken into consideration? Robots, action and recognition, sensors and actuators, and A to D converters. D to A converters are also a part of these embedded systems. Here we have to take into consideration the main aspect is real-time dependability. And the next is pervasive ubiquitous computing. It is the distributed systems, embedded web systems. Now, and development of design and development aspects of cyber physical systems are specification and modeling, embedded system hardware, embedded system software, evaluation and validation, mapping of applications to execution platforms, optimizations, and robot testings and robust testing. So while designing any cyber physical system, embedded system, we have to follow these steps, and how these steps are, what are their purposes, what are the different parameters we have to take into consideration, we'll see in continuation. Specifications and modeling. So before considering the specifications and modeling, let me show you what are the different blocks of hypothetical design flow. Design flow starts application knowledge, specifications, embedded system hardware, system software, could be RTOS, middleware, and so forth. Then we have to integrate with the design repository, and we have to take into consideration evaluation, validation, application mapping, and optimization. After performing these tasks in design flow, we have to get, or we will get, the design actual prototype of that cyber physical system. And then after completion of that prototype of the cyber physical system, then we have to test. Why to consider the specs and models? If sometimes something goes wrong with the specs, then it will be difficult to get, wasting a lot of time. Typically, we work with models of the system under design. So before directly starting design of cyber physical system, actual hardware and software, we have to model it to understand its behavior, to understand different aspects of workings and options of that system by taking into consideration parameters such as input, processing, and output. Then what is the model anyway? It is defined as a simplification of another entity, a physical thing or another model. It contains exactly those characteristics and properties of the modeled entity that are relevant for a given task. It is minimal with respect to a task if it does not contain any other characteristics than those relevant for the task. What are the requirements of specifications and modeling techniques? Multiple requirements while taking into consideration the specifications and modeling techniques. Programming elements, executability, support for design of large systems, readability, portability and flexibility, termination, support for non-standard input-output devices, non-functional properties, support for design of dependable systems, non-obstacle for efficient implementation, and adequate into consideration these requirements while phrasing specifications for modeling. What are the different characteristics of cyber physical system which we are supposed to take into consideration? The first one is reliability. It is the probability of system working correctly provided that is working at instance of t. Next one is the maintainability. It is the probability of a system working correctly d time occurred. Third one is availability. Probability of system working at time t, whether the system is available for performing that process or not. Safety, no harm to be caused. That into consideration different aspects of safety of that cyber physical system as well as the person who is operating that cyber physical system. Both things are important while designing any cyber physical system. Last, security, communication. In previous class, a previous lecture, Mr. Amit, he explained about the importance of medical data and why it is not ported onto the cloud computing because of the confidentiality of the patients as well as hospital. Even perfectly designed system, if the assumptions about the workload and possible errors turn out to be wrong, making the system dependable must not be an afterthought. It must be considered for the very beginning. So first one is the efficiency. Why do we need to design any efficient system? These are needed because of the code size efficiency, runtime efficiency, weight efficient, cost efficient, and energy efficient. Before designing any cyber physical system, we have to take into consideration these aspects. Next one is the energy efficiency. So while designing any cyber physical system, we use different processors, computing platforms, microcontrollers. So how these computing platforms, microprocessors, embedded systems, microcontrollers are designed? They are designed based on different technologies. And these technologies are ASIC, FPGA, DSPs, MPU, RISC, so on and so forth. So if you see this section, ASIC are more efficient as compared to the other platforms of microprocessors, MPUs. However, ASICs are application-specific integrated circuits. So designing ASIC is a little bit difficult task. However, those are more energy efficient. FPGAs, these are the reconfigurable computing platforms. We will see in continuation what are their advantages. DSP and MPU, these are a little bit expensive platforms. However, you can program these platforms as per the requirement of cyber physical systems. Hello, am I audible? Okay, thank you. Now we will see EPS and embedded system hardware. So this is the building block of any cyber physical system hardware. it is called as hardware in loop. So this hardware in loop is consisting of different blocks. First block is physical environment. Then how do we get different information, data, this physical environment? We need sensors. How do we take sensors data into the computing platform? We need two different important blocks. First one is sample and hold circuit, and another is A to D converter. So we have to data into the discrete form needed the information processing system. And lastly, we need outputs for displaying data or results to the end users and take actions, control actions with the help of actuators. Okay. Now we will quickly see few of the characteristics of designing of cyber physical system, and then we will move to hardware, software, and of designing of cyber physical system. What are the real-time constraints of designing of cyber physical system? A real-time system must react to stimuli from the controlled object within the time interval. So if this is the time instance said to be executed, that process at that instance of moment, it should respond at that instance of moment. If we give stimuli here and the process happens here, then it may not be useful, and there you will observe a time lag or latency. So for designing any cyber physical system, real-time constraints must be taken into consideration. Real-time constraint is called hard. If not meeting, that could result in a catastrophe. All other time constraints are called soft. A guaranteed system response has to be explained without statistical arguments. For cyber physical system, for some embedded systems, real-time behavior is less important. For CPS, real-time behavior is essential because it involves monitoring data, estimating the data, predictions, and then take the control actions. So all these processes happen inside the cyber physical system computing platform to take the action or to control the cyber physical system. CPS models also include a typically, CPS are reactive systems. What is a reactive system? It is one which is in continual interaction with environment and executes at a pace determined by that environment. Behavior depends on input and current state. Automata model is the appropriate way of considering these states into the real-time reactive systems. Model functions are inappropriate. And for this, we have to take into consideration hybrid systems, that is analog and digital one. What are the dedicated systems? Dedicated towards a certain application. Knowledge about behavior at design time can be used to minimize resources and to maximize robustness. Dedicated user interface and situation is slowly changing here. Systems become less dedicated. So let me give you an example of designing a cyber physical system by taking into consideration dedicated system and reactive systems. So if you see a riding of a electric tricycle or electric bicycle, then it is running on different road conditions. Then on these road conditions, rider is giving input of speed control using throttle and other input electromechanical brake. So if rider is riding and some object is coming in between, then rider has to take priority action of applying the brake. So how would rider decide what kind of input is provided to the control system? It is the behavior of that dynamics of application of the brake, stopping the release of the electrical control given to the motor, and at the same time stopping the release of the controls to the motor. So here priority is given to the brake action, the control system, and the control of the input speed is stop. So that kind of dynamics we have to take into consideration while designing any control in the cyber physical system, and that dynamics is very, very important. Leads to corresponding challenges. What are the different challenges while designing any cyber physical system? Dependability, efficiency, hardware properties, physical environment, meeting real-time requirements. So these are the aspects we have to take any cyber physical system. Dependability, what do you mean by dependability? Dependability is mainly associated with dependency on what kind of hardware you are selecting, whether that hardware is available, and what is its absolute duration. Is you have to take into consideration hardware and software whose support is available for longer time. Efficiency, are these hardware and softwares efficient enough by considering into energy efficiency, code efficiency, and other aspects. Hardware properties, physical environment. So whether the selected hardware and software is efficient enough to work in different temperature zones, like low temperature zones, high temperature zones, vibrations, environmental conditions, and so forth. Meeting the real-time requirements, whether the selected hardware and software is performing fast enough, is the main requirement of real-time execution of that task as per the cyber physical system. So these are the challenges which leads to the corresponding characteristics. What is the design flow? How would be the design flow of any cyber physical system? So this block diagram I have already showed to you, and I have described what are their different functions. Now we will see iterative design 1 and how would we design any cyber physical system, and how do we start and reach to the manufacturing level. First, we have to take into consideration specifications model, and then next step is the simulation architecture explore, evaluation and validation we have to perform. The next is the architectural model. Again, subsequent step is simulation of communication synthesis. After completion of these tasks, validation. Next is the communication model, hardware compilation, software compilation, their evaluation and validation has to be performed, then implementation of the model, and then manufacturing. Iterative design 2. Here require analysis, system architecture, system design, software architecture, software design, unit test, integration test, system integration, and acceptance and use. So we have to follow these steps of iterations of design while designing of any embedded system for cyber physical system. Now we will quickly see different aspects of embedded system: hardware, software, evaluation, validation, optimization, and testing very quickly. As I mentioned earlier, embedded system hardware is nothing but hardware. CPS control systems are considered in hardware in blue. The next component is sensor. Sensors generate continuous sequence of analog values. So these continuous sequence of analog values are not useful while processing it into the any information processing unit. So we need to convert these continuous sequences into the discrete sequences. And how do we get those discrete sequences? With the help of discretization. It processes discrete sequences or streams of values. Incoming signals in this domain must be converted to signals in in the discrete domains. This is the purpose of sample and hold circuit. So we have to use sample and hold circuit to convert the continuous signal. Each of the values stored on the capacitor as shown in this figure can be considered as an element of a discrete sequence of values h of t. So a clock signal at the base of this transistor enables E of t to be converted, or E of t is the voltage of E of t is considered as h of t. The capacitor gets charged. Once the signal is taken low, then h of t, this h of t is recorded with the help of A to D converter. So this is the purpose of A to D conversion from analog to digital values taken for the processing into the computer. Next block is the processing unit. There are different processing units considered in the cyber physical system. The first one is the application specific integrated circuits. These are specially designed integrated circuits for performing specific tasks. Digital ICs and different ASICs, application specific integrated, are available for performing specific tasks. Let me give you one example. If you want to control a motor, you have to just apply a PWM signal with the help of any clock circuit or any small microcontroller. The application specific IC takes into consideration all the commutation sequences as well as driving capability to drive the MOSFET gates to rotate the motor. So these application specific ICs are available in the market, making designers' life very easy in the cyber physical systems. Next processing unit is microprocessors or microcontrollers. One can consider microprocessor low end if the application is low end. For high performance applications, domain specific processors like DSPs and application specific instruction set processors can be considered. Next component is FPGAs. Full custom hardware chips ASICs are too expensive mentioned over here. Software based solutions are too energy consuming. Reconfigurable logic provides a solution if algorithms can be efficiently implemented in custom hardware. So if ASICs are expensive, then one can go for FPGA cyber physical system. These are fast as a special purpose hardware, but in contrast to special purpose hardware, the performance function can be changed by using configuration data. Reconfiguration logic finds applications in areas where fast prototyping and low volume applications are defined. Next block is the communication block. For communication in embedded systems, several spatial requirements are considered. For all systems that need to meet real-time constraints, communication times must also be guaranteed. Respecting real-time constraints is feasible with appropriate arbitration techniques for communication media. For example, time division multiple access TDMA is superior to a pure priority-based arbitration in this respect. Efficiency of communication hardware is frequently an issue. So what is the main issue of efficiency? It is the power required for communication media. And last, key role. So for designing any cyber physical system, communication is very, very important between embedded system and cyber physical system. D2A converters, we need D blocks because we have to control few of the actuators in the cyber physical system. Analog output devices, digital information must first be converted to analog. D2A converts the digital data into the analog form. A standard design uses weighted registers to generate a current which is proportional to digital number. This current is then turned into a proportional by using operational amplifier. And why D2A converters? As I mentioned earlier, to drive the outputs. Output devices of embedded or cyber physical systems include displays and electromechanical devices, also called actuators. They have a direct impact on the physical system. So what are the different softwares needed for designing any cyber physical system? These softwares are mainly needed operating or functioning of embedded system. And these are embedded operation systems. There are standard components that can be reused. For designing any cyber physical system, we need not have to start writing softwares in a language and C++. We can reuse different blocks in the form of libraries and APIs. Include system software. These include system software components such as embedded operating systems, real-time databases, other forms of middleware. What do you mean by middleware? It denotes intermediate layer between the OS and application software. User can call standard software components which may already need to be included in the specification. APIs, information of the application programming interface of these standard components may already be needed for completing executable specifications. So instead of starting from the scratch, user can start with middleware softwares, which is bridging the gap between embedded system and application software. And what are those middlewares? Those various software available in the market. Any software in between the operating system and the application software is called a middleware. Communication software may be the most important type of middleware. Such software supplements the communication features. Examples of these middleware in Cobra extends. Cobra is one of the middleware software which extends object access in object-oriented programming to remote objects. Another example is MPI, message passing interface, for communication between different processors. POSIX is another example or library available, which is an application programming interface to threads at the operating system level. A set of threads can be run in address space. Therefore, communication can be based on shared memory communication. And other middleware softwares include OpenMP and JXTA. So let me explain about what are the real-time operating systems and their requirements. Operating systems, cyber physical systems must be real-time operating systems. A real-time operating system is an operating system that supports the construction of real-time systems. What kind of properties a real-time operating system should follow? Timing behavior of the operating system must be predictable. Means we have to take into consideration the timing behavior. Operating system must manage the scheduling task. Scheduling can be defined as mapping from the set of tasks to intervals of mapping to start times as a special case. Some systems require the operating system to manage times. This management is mandatory if internal processing is linked to an absolute time in the physical environment. So, for designing any cyber physical system, the real-time operating system plays very, very important role, and we have to take into consideration timing behavior and scheduling tasks. Next,
சாக்கடைக்காரர் இருக்கார்ல கட்டு உங்களோட வாக்கிங் வருவார்ல ராஜோக்கு
Next.
பக்கத்துல ராஜ் ஆமா அவருக்கு இன்னொரு தங்கச்சி இங்க இருக்கும் அது யாரு கல்யாணம் பண்ணி
next block is evaluation and validation. The purpose of evaluation and modeling validation is design processes. we will have to validate and evaluate designs at each and every stage. I have shown during my slide design iterations. Design iterations, after completion of each block, design of each block, validation and evaluation is performed. Validation and evaluation, before we talk about the design steps. Validation and evaluation, even though different from each other, are very much linked together. What is validation? It is the process of checking whether or not a certain design is appropriate for its purpose, meets all constraints, and will perform as expected. Evaluation, it is the process of computing quantitative information of some key characteristics of a certain design, objectives, and possible partial designs. Now, next is the execution platforms. Mapping applications to execution platforms is a key activity in design of cyber physical system. A characteristics of embedded system that both hardware and software have to be considered during their design. Therefore, also called hardware-software co-design. The goal is to find the right combination of hardware and software, resulting in most efficient product meeting the specification. Then what is the definition of mapping application? It is use cases describing how the applications will be used and a set of possible candidate architectures, including possible heterogeneous processors, heterogeneous communication architectures, and possible scheduling policies. Find a mapping of applications to processors, appropriate scheduling techniques, and target architecture. These mappings should respect and objective functions such as performance, cost, energy consumption. Building blocks of mapping are standard scheduling techniques, hardware software partitioning, and advanced techniques for mapping sets of applications onto processor systems. Next aspect is optimization. Due to the need of embedded systems to be efficient, many optimizations are used in embedded system design. And there are different classes of optimizations. The first one is software optimization. Why do we need software? Software can be transformed by source-to-source transformations, such as the generated program can be implemented more efficiently than the original program. An example is include floating point to fixed point transformations. Software optimization transformation plays very important role in the optimization techniques. You might have come across various IDs available from various manufacturers. They provide free softwares as well as commercial softwares. Free softwares are most of the times are not optimized as per the requirement of design of any end system. However, if we go ahead with different packages of commercial ID software, then we will get these optimization tools, which is very useful for designing of any cyber physical system. So designing of any commercial cyber physical system has commercial aspects of uses of their tools, design tools needed for designing of software as well as embedded system. Hardware optimization for certain classes or special purpose hardware can be designed. As I mentioned earlier, motor control drivers, earlier we were designing with the help of H-bridge, with the help of transistors and MOSFETs. Nowadays, ASICs are very easily available, and even can use those application specific ICs for designing of any motor, designing of any system based on the motor control. Runtime optimizations. There are techniques which change the behavior at runtime in order to become more efficient with respect to is considered. Examples include dynamic voltage scaling, dynamic frequency scaling, and dynamic task. And last block of design aspect of cyber physical system is testing. To make sure that a manufactured embedded system behaves as intended, testing can be done during or after fabrication, and also after the system has to be delivered to the customer. That is the field testing. Why do we need to take a special attention, and what are different reasons? Embedded cyber physical systems integrated into physical environment may be safety critical. Therefore, their malfunctioning can be much more dangerous than malfunctioning of any official equipment. Testing of time critical systems must validate the correct time, means testing only the functional behavior is not sufficient. And lastly, testing embedded cyber physical systems in their real environment may be dangerous. Let me give you one example. If we want to test any cyber physical system associated with any nuclear plant, we have to think many times before performing that test, because it is in the dangerous environment. So if organizers permit me another 10 minutes, I can speak on case studies of cyber physical system based water purification and recycling systems. I like to show all the audience about the cyber physical system available in Siri. Shall I continue for another 10 minutes? Anyone? Thank you so much. Thank you. So, as a case study, let me explain you about what are the different research we have performed in designing of cyber physical system, especially for purification of water. CSR Siri Pilani and CSM CRI Bhavnagar have jointly developed, remotely monitored and controlled high capacity RO plant for desalination of seawater. So it is a complete plant which designed jointly between CSM CRI Bhavnagar and Siri cyber system, and CSM CRI Bhavnagar team developed physical system, and both teams work together to come up with a cyber physical system to have or to derive a remotely monitored and high capacity RO plant for desalination of seawater. Project was aimed at design and development of automation for high capacity RO plant for desalination of seawater. The monitoring and controlling of the RO plant on wireless communication and embedded systems. A handheld embedded water parameter measurement system and embedded backwash controller were also developed and tested during the project work. So this is the block diagram of the cyber physical system which we implemented with the help of our sister laboratory. So physical system consisted of membrane modules, various pumps and valves fitted in the plant. The plant is assembled, fabricated and constructed at CSM CRI Bhavnagar. Plant is remotely monitored and controlled. Here remotely monitored and controlled is nothing but your automation, which is the cyber system, using embedded controller unit, real-time unit and embedded controller software developed in lab unit. If you see this part, this is the purification of desalination of seawater. This is the automation done with the help of computing platform. We used microcontroller platform, 16-bit microcontroller along with various drivers and sensing systems. And this is the complete platform of cyber system which we developed for the desalination of RO plant. Dashboard which we developed in LabVIEW software for monitoring, recording and storage of the data from the plant. So various parameters we monitored Those are conductivity, TDS, pressures, pH, temperature, turbidity, flow. These parameters were recorded in real time with date and timestamp and stored into the file for further analysis. So these are the other dashboards which give the control commands or operating the plant in different modes. The water purification plant operates in different modes and we have to release the command accordingly. So this screen is showing the purification plant, and this screen is showing remotely monitoring and controlling of RO plant using LabVIEW Internet Toolkit. So the same dashboard was made available onto the browser, and from browser anywhere in the world one could able to operate the designed plant at DCSM CRI Bhavnagar. Few of the parameters which we recorded are shown over here: conductivity, TDS, temperature, pH, and so on and so forth. So another smart system which we have in our CSR Siri campus. So for designing of that cyber physical system for smart water grid, we have considered water quality parameters, control parameters, and process. Water quality parameters are mainly associated with pH, TDS, so on and so forth. Controlling parameters are mainly associated with controlling various valves, pumps fitted into the plant, and process conditions are mainly associated with set points, leakages, water pressures for RO membrane, UV exposures, efficiency, condition of various subsystems, hydraulic conditions, stress and corrosion, etc. This is the basic block diagram of smart water network for community usage, which we have designed while designing of our smart water grid. It is consisting of, if you see, various filtering stages, real-time and increased granularity water data, technologies which we used for designing of this smart water grid involves data acquisition and integration, data and storage, management and control using SCADA software, hydraulic modeling and analytics, monitoring, fault detection and localization, visualization and decision support. So we have this physical system and this integrated to get or to realize the cyber physical system in the form of smart water grid in our laboratory. And we are using this cyber physical system for water demand side management experimentation, hydrolysis, and leak control analysis. So this is the image of cyber physical system, two-layer cyber physical system of smart water grid available in our laboratory. It is a test rig of pipes, various sensors, valves, pumps are fitted on this, and different sensors and their numbers are listed in this table. If you see, we have used 8 pressure transmitters, 3 temperature transmitters, 14 ultrasonic flow meters, and so on and so forth. These are other views of smart water grid test rig in our laboratory. This is the closer view of lower layer of the plant and the plant, wherein you can see various ultrasonic sensors are fitted for generating the data for analyzing the billing systems or understanding the billing, developing the experimentation on billing system of the water supply. Along with these pipe structures, we have SCADA platform, wherein we implemented SCADA platform and PLC system, wherein we have dashboard and control for this test rig of cyber physical system smart water grid. So with this case study of purification of water of desalination of seawater using RO system, which is wherein we implemented remotely monitored and controlled automation technique, and another case study of CPS smart water grid. I am concluding today. So in this lecture, we have seen different design aspects of cyber physical system from embedded system design point of view. We have started with specifications and modeling, then subsequently requirements of specifications and modeling. Then we have seen embedded systems designing, system softwares, especially real-time softwares and middlewares needed for designing of any cyber physical system. We have seen purposes and importance of evaluation and validation, and subsequently we have seen optimization and testing needs requirements in designing of cyber physical system. Lastly, we have seen two case studies on water purification systems as a cyber physical system in our CSIR series planning. So these are our in smart water grid associated with smart water grid control systems and CPS. CSR Siri SEG group welcomes faculties, students to contribute in the ongoing research projects in Siri lab under programs. Your offline online contribution in research is. Thank you. I would be very happy to take few questions. Let me stop sharing. Yes, stop sharing. Great. There are few questions. Is there any open source simulator? Wait a moment, something. Yes, is there any open source simulator circuit designers to simulate or test our embedded design circuits before going to hardware? Yes, MATLAB provides. Very recently, MATLAB has created various tools of designing of CPS. So you can use MATLAB for simulating any cyber physical system. There you will get simulation of hardwares, embedded hardware used from various industries like Texas Instruments, Microchip, so on and so forth. Wait a moment. Could this system be incorporated for various applications? It is the automation based on the embedded system, which is the low end, mid end, and high end platforms. So you may use microcontroller platforms, 8-bit, 16-bit, and 32-bit processors, along with real-time operating systems based on the requirement of designing of any cyber physical system. Any other questions? Audience may unmute and ask question directly. I would be very happy to answer them. You may unmute and ask question, or you may type in the chat box. Someone is asked open source, not licensed one. See, if you use open source, yes, there are few platforms of simulation of cyber physical systems which are open source, like the speakers talk about open source platform of ARPANET. So you can use ARPANET software to simulate the physical environment, get the data, and then after getting that data, you can use Python, so and so forth open source platform, and predict the results and predict the behavior of the physical system before start designing of hardware and software. So you can use Ethernet as a physical for and simulation, and Python software for analyzing the data. Any other question?
So there is another online question. Could this system be incorporated for various applications?
Yes, it can be possible to incorporate this system to various applications. So as I mentioned earlier, before designing any cyber physical system, we have to write down specifications and we have to develop the model. These two steps are very, very important before starting physical designing of your hardware and software. So if you have knowledge of deriving the specifications, modeling the system, if you derive the behavior of that physical system in terms of mathematical modeling, simulation tools, and get the preliminary data, then that certainly builds the confidence and take it ahead to start the building of the embedded system for cyber physical system. Yes, it can be applicable for various applications also. As I mentioned earlier, I have showed the cyber physical system for water purification systems, RO automation, desalination of RO. For other applications, like yesterday, one of my colleagues talked about air quality monitoring. So air quality monitoring and displaying the data, predictions, performing the predictions. Yeah, kind of platforms. Embedded system is the core foundation of designing of any cyber physical system. One side you have embedded systems, and in previous lecture you have experienced high-end platforms from NVIDIA. So we cannot bring NVIDIA platform and fit it to the water purification plant. Water purification plant itself costing 1 lakh rupees. So if we invest another 1 lakh rupees on automation of water purification plant, it will be very expensive. We can think other embedded system, possibilities of other embedded systems, so as we can give quality of automation as similar to the high-end platforms, and still we can fulfill the requirement of automation of any purification plant. And it is also applicable for designing of any other automation in the segment of cyber physical system. So if you are aware, nowadays IoT devices, microcomputing devices, 16-bit and 32-bit, your Raspberry Pi platforms, your other boards, fanless PCs, and AI techniques. These three platforms are very easily available, and these platforms are cheaper platforms to design any cyber physical system. And only thing is that you have to follow these design aspects before initiating your design.
So, there is another question.
Yes.
CPS is more than all decade old. What are the drivers which are bringing it to limelight now?
Can you please repeat question?
Yes, sir. CPS is more than a decade old. What are the drivers which are bringing it to the limelight now?
This is not clear. Can you please text your question in the chat box? Meantime, I'm answering another question.
Yeah, okay, sir.
Please text. The next question is, can we design any CPS system for underwater applications? How we can get data in same applications? Yes. Designing cyber physical system for underwater applications is a challenge, and main challenge is communication. One has to see what are the different possible hardwares, communication hardwares and platforms are used for underwater communication. So it may be a hybrid platform, maybe wired communication platform, but those platforms are very sophisticated platforms, and you have to see what are the IoT platforms mainly designed for underwater applications. Okay, so communication platform is a big challenge. Water communication, hardware platform, hardware embedded system, and softwares, real-time softwares. These are not very difficult platforms for designing underwater applications. But communication, yes, communication platform is a very and you have to see what are the sources, what are the devices available in the market with defined specifications which you can use for designing cyber physical system for underwater applications. Next question is, are international standards for interfacing, communication, control, and physical components which HDOs are working on it? Okay, yes, certainly there are standards for designing of any cyber physical systems, especially communication, control, and physical systems, and we have to follow those standards, especially defined in IEEE. Yes. And after completion of your prototype of cyber physical system, you have to get it certified from standardization laboratories, like to go for standardizations of various standards like IEC standards, environmental standards, vibration standards, and so on and so forth. You have to get the certification of that cyber physical system. If you don't have that certification, you cannot deploy that cyber physical system for end use. Okay, and you have to take into consideration IEEE standards for designing of cyber physical system. CPS is a decade old. What are bringing to limelight now? I strongly agreeing with this this statement of Nitya. CPS is a decade old, and what are the drivers? Certainly, these are the old techniques. However, because of the introduction of the other technologies like IoT, state-of-the-art embedded systems, and AI techniques, these three components are enabling us to see our earlier perspective of designing of embedded system as a cyber physical system. Earlier, we were talking about embedded system, designing of embedded system for specific application. Now we are talking in terms of designing of cyber physical system for a specific application. Let me give you one example of cleaning robot, very recently introduced in the market. So that cleaning robot at every customer's home, we can program it very easily using your mobile app. So cleaning robot at our homes are nothing but what? They are the cyber physical systems. You have an electric vehicle. It is connected with your mobile app. It is a physical system. Are not these cyber physical systems? These are cyber physical systems. Earlier, we were talking about the cyber physical system, bigger level, industry 4, then smart cities. Yes, people and developers are using cyber physical systems at high-end side. Nowadays, due to availability of IoT, embedded systems, and AI techniques, people are started developing small applications around cyber physical system. I hope I have answered Nitya's question. Then, how the processes should be chosen to satisfy CPS? If I interface deep learning and MATLAB simulating, how my processes should be? Can you specify any specification for the processor? Yes, certainly. If you are defining processes, you have to take these processes at the time of freezing your specifications, and you have to take into consideration time and their concurrency to achieve the real-time aspect while executing. Okay, and for that you need a real-time operating system, and you have to apply the scheduling mechanism to ensure all these processes are running in real time. So if your process is complicated, if you are using AI techniques, then you go ahead with the 32-bit processors available in the market with different speeds and available RAM memories, available memories for full the execution of your processes as per your scheduling algorithms and execution of those processes, generation of the control actions. All these things happens in real-time mode. So you have to freeze your specifications, you have to decide the hardware platform, and accordingly you have to write the real-time operating, you have to use the real-time operating system to write the application software for these processes. Rita, I hope I have answered your question. Can we specify any specification for the processor? Yes, you can use applications, few of the available ASICs along with your embedded system or any embedded processor for ease in designing and achieving your real-time goal of designing of any cyber physical system. Shall I move to the next question if time is permitting, organizers?
Yes, sir.
Can you
Yes,
speak
sir.
loudly?
Yes, sir.
There is one question, shall I answer?
Yes, sir. Yes, sir.
In development of CPS, okay, development of CPS are in development of CPS, okay, are you recommending to use standard development boards like Raspberry Pi, etc., to use custom to bring them to market? So yeah, this is very important question. Audience, please make sure what I am telling you. Earlier we were using 8085, 8051, then ATmega processors, peak processors for designing our custom-made boards. But these custom-made boards are not sufficient to fulfill the requirement of real-time operating systems, scheduling algorithms, middleware softwares. So we have to take the advantage level boards as similar to the Raspberry Pi and so forth. Okay, we should use them. We should use them because we don't have to design a complicated microcontroller, 32-bit microcontroller board, then drivers around it, signal conditioning circuit needed to capture the sensors data, and then the generation of actions with the help of drivers. So if you ask me, I would suggest all of you to use to use the available boards in the market instead of custom PCBs. Okay, so these boards are available in the market. Application APIs are available, middlewares are available. So make use of these tools to test it initially in the and demonstrate your cyber physical system. Then after designing of that cyber physical system, you go for evaluation and validation, mapping of application to the embedded system and softwares, mapping of applications to the hardware software, and optimization and testing. Then you go for final prototyping. So it is the design iteration process which you are supposed to perform. If you spend more time in designing of your custom board, then you cannot reach and achieve your goal. Are available, hardwares are available, software middlewares are available. Make use of these tools and start designing. Take into consideration your design aspects. How can you fit your design with the help of available embedded systems, available real-time operating systems, middlewares, and APIs, and build system around it to achieve a goal of designing of any cyber physical system. Yes, let me add one more point. Customized own boards. So you need not have to develop the complete customized board. You can use embedded hardware and design your customized board, which is needed for signal conditioning and generation of the drives. So your embedded system board, let's take an example of a Raspberry Pi, but would sit on the custom board as a computing platform. And that bottom board, customized board, would be the motherboard, as similar to a CPU PC. So I believe I have answered Aditya's question. In that case, development boards can. Thank you so much for listening, giving me opportunity for speaking on design aspects of cyber physical system. I understand this topic is bit challenging, bit complex. However, I cover all the aspects of design of cyber physical system in this talk. Thank you so much, organizers, for giving me opportunity. Over to
So
you.
thank you, sir. For the token of love, we'd like to provide a e-memento for yourself. So I request you to kindly accept it.
For memento.
Yes, sir. So it's been displayed in the presentation.
Yes, it is displayed.
Thank you, sir. Thank you so much, sir.
Thank you. Okay. What?
A very good afternoon to all. I welcome you for this third session on second day workshop. The speaker for this session is Mr. Ramachandran, sir. I'm really happy to introduce our speaker, Mr. Ramachandran. Mr. Ramachandran is a principal consultant in the thought leadership team in Infosys, the Knowledge Institute. He is the lead for manufacturing and engineering domains. He has more than 25 years of experience in digitization for industrial applications. His current topics of interest are Industry 4.0, sustainability, servitization, and future of work. He is a regular blogger and speaker on these topics. He has co-authored hello, am I audible?
Yeah, we can hear you now. It was broken in between.
Sir, yes, sir. Mr. Ramachandran is a principal consultant in the thought leadership team in Infosys, the Knowledge Institute. He is the lead for manufacturing and engineering domains. He has more than 24 years of experience in digitization for industrial applications. His current topics of interest are Industry 4.0, sustainability, servitization, and future of work. He is a regular blogger and speaker on these topics. He has co-authored a book titled Neo-Skilling for Digital Transformation, along with Professor L. Prasad, IIM Bangalore. He is a mechanical engineer with a master's in production engineering and has executive MBA from IIM Bangalore. We welcome you, sir.
Thank you so much. Am I audible?
Yes, sir, you're audible, sir.
Okay, good. So can I start my session?
Yes, sir.
Okay, good. Thank you so much. Good afternoon, everyone. Thanks to Professor Devraj and the other organizers for giving me this opportunity to talk about Industry 4.0. So as you can see from the agenda, the rest of the topics that have been covered in this today workshop are mostly technical in nature. But my session will be slightly different from that. I will talk about a maturity index we have developed for Industry 4.0. Industry 4.0, as you know, is a complicated topic. In fact, you can even call it an umbrella term for all the technologies that you have been covering in these 2 days. So it is not one single technology. It is a basket of multiple technologies. In fact, it goes even beyond technologies. If you look at large organizations which find it challenging to implement Industry 4.0, to adopt Industry 4.0, they face cultural challenges. You need to undergo process re-engineering, business process re-engineering. So that is why Infosys, along with a consortium in Germany, came up with a framework and a maturity index, because organizations struggle to understand where they are in Industry 4.0 journey. How can they plan their road forward? How can they benchmark themselves against best-in-class companies? So that's where a maturity index is very important to make sure there is proper adoption of Industry 4.0. So this framework was developed by Infosys. I'll share more details about the consortium. We looked at 4 different dimensions for this maturity index and the framework behind it. So not stopping the technology, we also looked at process, we looked at cultural aspects, we looked at the resources aspect. And this index was first released sometime in 2015, 2016 in the Hannover Messe Industrial Fair. But now we are again using this framework to estimate the maturity level of different industries, different industry segments globally. We're doing this study in India and also in other regions. We are doing this in collaboration with IIT Madras and with the University of Nottingham. So these are still in earlier stages because Industry 4.0, as you know, is a very dynamic topic. A lot of advances are happening in it. Organizations are at different levels of maturity in adopting it. So we're again going through a new round of estimating the maturity of different organizations using this framework. So let me share my screen. And we also look at Industry 4.0 from multiple perspectives. So the most obvious one is manufacturing, because it is very widely adopted in the shop floor. But we can also look at it from maintenance, for example. We can look at it from a services perspective or energy or even sustainability perspective, because sustainability is a very hot topic today. So there are such multiple perspectives, and you can use that to find out where is the weak spot. Traditionally, manufacturing could be the strongest area where Industry 4.0 principles are practiced, but it is very much applicable in other functions in an enterprise also. And it is not limited to manufacturing alone. It can be practiced in healthcare, for example. It can be practiced in retail. There are other industries too where Industry 4.0 can be practiced. So with that, let me share my screen. Can you see my screen?
Centigrade or degrees Fahrenheit, right? So that can.
Okay, so let me continue. So the topic for this session is Industry 4.0 maturity model. So this is the agenda for the talk. We'll start with a brief overview of Industry 4.0. All of you know what it is about. You are the experts in Industry 4.0, but just to set the context. And then we will come to the ACATEC framework. So this is the framework which we came up with. This is the consortium that I mentioned initially. So ACATEC consortium along with Aachen University. I'll show you the participants with whom we have come up with this framework. And then we'll specifically look at Industry 4.0 in the post-pandemic era. Because in my opinion, organizations that took Industry 4.0 seriously before the pandemic would have definitely benefited from it. We will look at specific scenarios where the industry had to change because of the pandemic, and we'll see how those who were early in adopting Industry 4.0 would have benefited from it. And then we will look at Industry 4.0 from an Indian context. So this is not something applicable only for developed countries like Germany and in the West. It is very much applicable in India too. We can adopt it according to our local conditions. I'll give you some examples, some where I was personally involved, where Industry 4.0 has been effectively adopted in India too. And finally, we look at what to automate. So this here, I've borrowed a concept from the book about reskilling, which I wrote with Professor Prasad, because Industry 4.0 eventually talks about autonomous systems. We are talking about working without humans, but that's not the intent really, right? So today, companies call what is called the triple bottom line or the 3 Ps. It's not just the profitability or the bottom line that's important, but responsible organizations look at their people side of it. They look at the planet side of it from a sustainability perspective. So that's where we will look at a framework to see where can we stop, what sort of tasks should be automated. Do you want to reach a state in a country like India where a factory is completely run without humans? That's not the point. So we look at where to draw the line between what to automate and what to keep with manual sessions, with manual work. And if time permits, we'll have a Q&A session. So this is the agenda for today. Like I said, it's a slightly higher level perspective from the detailed technical sessions that you have been having previously and you're going to have after this. So very quickly, what are the principles of Industry 4.0? This is as defined by the German government. The aspect I like here is that this is very technology agnostic. It does not say adopt IoT, adopt big data, or even analytics. It gives very simple things like you need interoperability. You need your machines, your humans, your processes to talk to each other. So obviously, when you map it to technology, it's going to be IoT. So start with interoperability, and then you need information transparency. Transparency today is very, very important post-COVID with all the supply chain disruptions that are happening. And you need to be able to simulate difficult scenarios before they actually happen. That's where technologies like digital twin help you. So you have information transparency to take rational decisions. Then you have technical assistance. Again, this is where analytics is used, where computers, algorithms, systems help humans to make informed, rational decisions by using data. Data can be visualized, can be aggregated. AI is going to help you there, but very basic is analytics. And you can also have decentralized decisions or autonomous decision making. Sometimes decisions have to be made very quickly. Sometimes a human may not be available. A delay in decision making can prove to be very costly. So that's where autonomous decisions, timely decisions without human intervention are very important. So these are the very basic principles of Industry 4.0, and we can map it to each of these technologies. So again, one more look at a structured approach. These are some of the topics that have been covered in this Work Today workshop on cyber physical systems. The beauty of Industry 4.0 is that it does not make any technology mandatory, or it does not exclude any technologies. Any technology that you can think of can be classified under one of these 4 buckets. So IoT, mobility, cloud, all those come under interoperability for communication. When you talk about transparency, we can use a digital twin, we can use mixed reality, augmented reality, virtual reality. Big data analytics, artificial intelligence help you for decision making, and similarly autonomous systems. And any other technologies that's left out, like additive manufacturing, quantum computing, technologies are going to keep growing or will keep developing, but Industry 4.0 will definitely find a place for it. It is not about the implementation of technology for the sake of it, but it has to make business sense. So that's where a framework helps. We need to look at what are the challenges faced by a business, what are the opportunities available for a business, and then implement these technologies accordingly, and not go for it just for the sake of adopting any technology. So one more way of calling Industry 4.0 popularly in the industry is what is called IT-OT integration. Traditionally, if you look at manufacturing companies, sorry, can you go on mute, please, madam? I think this, Punita, madam, can you please go on mute? Okay, can someone tell them, please? Okay, let me continue. So what is IT-OT integration? So traditionally, if you look at manufacturing, the shop floor has been a siloed function, so to speak. It's like an island within an enterprise. Communication between the shop floor and the rest of the functions was not very smooth. So that's where Industry 4.0 recommends what is called IT-OT integration. So there is seamless flow of information right from your suppliers, starting from your suppliers to your factory and all the way to your end customers. So if you look at the blue arrow here, that's the flow of your product. It could be an automobile. I've used several automobile examples in this presentation because auto industry, like any other technology, has been an early adopter in technologies, including Industry 4.0. So you will see a lot of you will see a lot of automobile examples in this Industry 4.0 presentation. So let's go through the blue arrow. You start with your suppliers. Suppliers provide you systems, subsystems. It goes into the factory. It gets assembled along with other components, and then it gets shipped out to customer. There are several IT systems involved in this flow, starting from your ERP system. For planning, you have a CRM, which talks to the customer, your supply chain management systems, MES on the shop floor. So Industry 4.0 recommends this IT-OT integration so that the shop floor is not siloed out from the rest of the enterprise, and there is seamless and smooth flow of information. So now let's get to this specific framework that I spoke about. So like I said, the Akatech consortium is an industrial consortium in Germany. These are the organizations that are part of it. So this consortium, Infosys was part of this development of the maturity index and the framework along with the participants of this consortium. So once this was published, this framework and maturity index have been used by several organizations. Akata consortium itself has published specific versions of this maturity index for Singapore industry, for example. That's a very recent one. I'll share some more examples. So these are some of the other partners who jointly work together to come up with this maturity index and framework. So like I said at the beginning of my session, Industry 4.0 is not just about the technology part. So we look at it across these 4 dimensions, starting with resources. Then we look at business processes, what is the organization culture, and finally the technology systems. Only when all these 4 work together, Industry 4.0 initiatives will be successful. So the people part is very, very, very important, because I have been part of several large IT applications in enterprises. It is the resistance to change that usually hinders the success of these large initiatives like Industry 4.0. And it's not like a rollout of an ERP or a CRM or a system, right? It has both hardware and software components. There is a multi-year roadmap that has to be implemented. So the cooperation of every individual in an organization is important. That's where culture is also important. So when we look at this maturity index, we look at these 4 aspects. We ask a participating organization questions to understand where they are in each of these dimensions and what are the levels of these 4. So that's where these levels help you. So these are the 6 levels we look at when we talk about a maturity index. If you look at basic computerization or automation, or let's call it Industry 4.0 itself, these are the 6 stages we look at. If you look at the left extreme, it starts with basic computerization. It starts with spreadsheets for calculation, accounting, this type of stuff. And then you have ERPs. And then you have connectivity, where there is basic internet, there is communication between systems. Most organizations today have these 2 levels of computerization or Industry 4.0. So from there, that's where the real Industry 4.0 journey starts. The first level is what is called visibility. So when organizations have visibility, you understand what is happening inside an enterprise. The what part is addressed. So you know what is the status of critical bottleneck machines. You know what is the status of critical material flow inside your factory. That's the first stage, where Internet of Things, as you know, that's the technology which helps you get visibility. But the maturity index, again, like I keep insisting, does not look at the technology part, but it looks at it from a business perspective. We'll look at examples where in the post-pandemic era, visibility has become very important for companies. Next is transparency. So we don't just stop with understanding what is happening, but we need to understand why is something happening. So that's where you need to do a root cause analysis. There could be a spike in certain parameters. We look at trend charts. There are control limits. When any of those limits are breached, then we raise alerts and we do a root cause analysis to understand why something is happening, so that you can take corrective action. You can take action before something that's really not required happens. The third level is what is called predictability, where you don't wait for these trend charts to tell you what's happening, but you simulate things. You try to predict what is going to happen before it actually happens. And the fourth level is called adaptability, where a system is able to do all these things. It has visibility, transparency, predictability, and it is also able to take a decision on its own without waiting for any human interaction. So that's where you reach a level of adaptability. So these 4 levels can be mapped to these 4 dimensions that I spoke about: resource, process, technology, and organization structure or culture. And that's how we come up with the maturity index. So just to give you an example, if you ask me where are most of the companies today, so this was I think a few years back, Akata Consortium published a study, and they said 80% of organizations globally are in the second stage, which is on connectivity. I think the situation would have slightly improved today. Here, as you can see, 4% of organizations are looking at visibility. I'm pretty sure there will be organizations which are at the extreme end, which are already having autonomous systems also. But in terms of percentage, it may be very less. Most companies today are still in the stages of basic computerization and connectivity. So let's look at Industry 4.0 in the post-pandemic era. So there was so much of hype around Industry 4.0 even before the pandemic. But when the pandemic struck, then there were so many shutdowns, there were supply chain disruptions. Organizations really struggled. But here are some scenarios which are an outcome of the COVID-19 pandemic. The first, as all of you know, is remote work, right? Because of the need for social distancing, many of us did not go to factories, did not go to our office. We had to work from home. That's where organizations which had invested in a connected world, in connectivity across their offices, across their factories, really benefited. So one example is Toyota. Toyota was able to roll out a new model of its Sienna van with most of its team working remotely. So as you know, automobile rollout is not just about design, right? It also has a lot of tests to be done. All those processes were followed, and all this remote connectivity helped them to make sure that they are able to roll it out successfully. So remote work is going to continue. You can call it hybrid work. So that's where, again, connectivity, which is a very, very basic tenet of Industry 4.0, is going to help you. The next scenario is the make-to-order model. Companies like Japanese companies like Toyota and Honda traditionally followed a pull model. They did not make cars based on a demand forecast, but they manufactured cars based on actual orders from customers. So if you look at post-pandemic era, there has been a severe chip shortage, as all of you are aware. So even US companies like Ford they were forced to shift from a make to stock to a make to order model. They did not have enough inventory of chips to have a demand forecast, make cars and stock them either at the dealer shop or in their own factories. Instead, they had to go with actual customer orders and make cars based on that. So that's the shift to make to order model. So Ford CEO recently said that they're probably going to continue with the make to order model. So where Industry 4.0 helps you here is that it helps status tracking. The moment you say make to order, a customer is going to place an order for a specific configuration of a car, and he or she is going to ask you for the status. Where is my car? When can I expect it? You need to give them a clear date. It may take longer than make to stock, but then you need to give a clear delivery date. That's where you need status tracking of each and every component of the car so that you can tell them the expected delivery date of the car. So Industry 4.0 principles are going to be very important in this make to order business model, which we're going to see following the pandemic. Then carbon emission measurement for sustainability. Sustainability, as you know, has three types of carbon emission. According to the greenhouse gas protocol, you have scope 1, scope 2, and scope 3. Scope 1, usually most companies have their hands around it. It is the carbon emission that comes from power generation that happens inside your factory. You could be running a generator, the transport vehicles that you run inside the factory. Scope 2 is equipment that is run using bought out electricity or power. That is also getting under control. But scope 3 is where the biggest culprit is. 70 to 90% of the total carbon emission, depending on the industry, comes from scope 3 emission. This includes your supply chain emission, that of your suppliers, your product usage in case of automotive industry. So unless companies really attack their scope 3 emission, getting to a net zero situation is going to be very challenging. Again, that's where an Industry 4.0 type of approach with visibility to carbon emission is going to really help organizations. Supply chain disruptions, again, a big fallout of COVID pandemic. So President Joe Biden recently announced an initiative called FLOW, which stands for Freight Logistics Optimization Works, where they're trying a pilot project where ocean freight carriers and other logistics players are going to share data with, let's say, retail players and with their customers, with their upstream and downstream stakeholders. They have realized that data sharing is very important to avoid, to identify supply chain bottlenecks and take timely action. So this type of, because this data was initially considered very protective, but today companies are looking at sharing supply chain data upstream and downstream so that bottlenecks can be identified in a timely fashion and some corrective action can be taken. Scenario planning, again, using digital twins is getting very popular in supply chain. And circularity, again, this is one more aspect of sustainability. There are several materials today like lithium, which are very, very rare on the earth. So companies are forced to reuse this material at the end of the life of products. And also responsible organizations don't want to throw away materials like plastic and create a dump in the earth. So circularity is becoming very popular. That's again where Industry 4.0 is going to help you. You can raise proactive alerts when a part or a product reaches its end of life. What is the material used? Where is it in the reverse supply chain? So these are some situations post-pandemic where an Industry 4.0 approach is going to help organizations. It may be too late to start working now, but better late than never. But like I said, companies which already made investments in these areas are going to benefit from it. So we looked at the principles of Industry 4.0. We looked at the maturity index, how it was done with the consortium. Now, like I said, these are not something concepts that are applicable only for developed countries, but even in India. So here are some examples. Before we go to the examples, what are the real challenges in Industry 4.0 adoption in a country like India? So this was a PwC study. It's a bit old, but it still makes a lot of sense. If you look at their first study that they did to understand what are the challenges in Industry 4.0, in 2014, it was about unclear economic benefits. What is the ROI? Why should I invest so much? Those were the type of challenges. And then in 2016, it slightly shifted into lack of digital culture, lack of training, support from senior management. These were the type of challenges. But in 2018, people became the biggest challenge for Industry 4.0 adoption or digital transformation. So if you ask me, this situation is still continuing. These technologies have already proved what they're capable of, as you can see from these sessions, other sessions that we have been seeing in this workshop. The technologies are affordable. They have already proved what they're capable of. Most organizations struggle in getting skilled people who understand these technologies and to implement them to make a meaningful business impact. Here is one more study from World Economic Forum to understand what are the challenges in Industry 4.0. So they looked at it across two axes. One was the drivers of production, the y-axis, and the other is the structures of production. The structure of production is what you already have today. It could be capacity to make, it could be capability. And if you look at drivers of production, these are slightly futuristic things like skill set, for example. And India, unfortunately, falls in this bottom right bucket, which is called legacy. So we have a strong base. India is very strong in manufacturing, but World Economic Forum sees a huge risk for countries like India in future. This was again post-pandemic, but it makes a lot of sense now, even after pandemic. So that's where sessions like this are going to be very important. Our education system is going to play a very big role in ensuring that new engineering graduates who pass out are aware of concepts like Industry 4.0. It is very multidisciplinary in nature. So at least this basic awareness should be there to make them industry ready. So if we really have to increase our GDP contribution from manufacturing, Industry 4.0 is going to play a big role, and the people part is what is most important for them. So here are some specific examples from India in successful Industry 4.0 adoption. The first one that comes to my mind is Mahindra's vehicle factory in Chakan. I had the privilege of spending a few days here. We did a case study. Cisco had sponsored it. Cisco has done the networking for this factory. It is a greenfield factory. We did the study almost a decade back, sometime in 2014 or 2015. But Mahindra had already thought about how a futuristic factory should look like. So here are some screenshots. So they had already developed a virtual replica of the factory to simulate situations. So they could do process validation. Robotics was deployed. They had virtual commissioning. It was like a software-defined factory. Many advanced concepts were already adopted. So this plant is in operation. They used to manufacture XUVs now. I don't know what it is used for now, but it's a very advanced factory. Metalman Auto. So you may think Mahindra is an OEM. Large organizations can afford Industry 4.0. But one more organization with whom I have been talking is Metalman Auto in Delhi. Metalman is a tier 1 supplier of sheet metal and tubular components for auto industry. They use a lot of robots for TIG welding, MIG welding, and they have connected these robots because it's very important for them to know the status of these critical robots. That's one more example. Again, Industry 4.0 is not a state to be reached, right? It's a journey that companies undergo because there is always scope for improvement. Already some people are talking about Industry 5.0. So that way, all these organizations have got onto the right path. There's still a lot to be accomplished, but they have seen the value of Industry 4.0 and continue to go along the path. Siemens switchgear factory in Maharashtra, this was again reported in the media. General Electric set up a multi-modal factory in Pune. They call it a brilliant factory. So everybody may not call it Industry 4.0. It can be called under different names. But again, from the maturity index perspective, we need to go back to the basics. Have they implemented visibility? Have they implemented transparency? Do they have predictability? Do they have levels of autonomy? That's the way you should look at it and then come to technology. Instead of saying, I have implemented IoT, I have implemented digital twin. That's a wrong approach to Industry 4.0. So from a maturity index perspective, look at it from a business impact and not from just a technology part. So some more two-wheeler automotive factories, Hero Motors, TVS Motors, I can keep on going. I'm sure the list is long today. This is not an exhaustive list, but just to give you an idea that Industry 4.0 is very much being adopted in India also. So some more examples here. This was in Bharat Forge. This is an example in Hyundai, where they looked at it as a risk to mitigation rather than an ad hoc investment. It helped them during the pandemic time. Eaton is one more example. So I will not go through the details of it. So we looked at Industry 4.0. The ultimate level in that is autonomous systems which can operate on their own. But like I said, what is the end state? Are we proposing that factories should be completely automated without any human intervention? That is not the case. Again, I reminded you about the triple bottom line. It's very important for us as a country, any country for that matter, to make sure we provide employment, because we don't want a completely capitalist society where big organizations make money and people are not employed. So employment is important. So that's where we propose this framework in the book on neo-skilling that me and Professor Prasad wrote. So if you look at all the jobs, all the tasks that are available in any organization, you can classify them into these 4 buckets. On the x-axis, you have a novelty or the amount of decision making. On the y-axis, you have programmability or the ease with which you can program a particular task, right? So if you take 2 levels as high and low for both these axes, and you take all the jobs that are available in an enterprise, on the top left is the jobs that are very low on novelty, but very high on programmability. These are very routine jobs. So as you know, these can easily be automated using robotics. And then if you come to the bottom left quadrant, these are jobs that are low on both programmability and on craft. These are very difficult to automate. You can call them as craft jobs. So I've shown a carpenter here, but there are craft type of jobs in any type of industry. It could be an architect in the IT industry. It could be designers. It could be testers in auto industry. These type of jobs will never get automated. And then there are professional jobs that are very high on both programmability and novelty. I've shown a doctor here. Artificial intelligence could do some of these tasks. I'm not saying AI can replace a doctor's job, but there are some jobs. For example, the US government has approved Google's app for retinal diabetics, for example. So it can take a photo of a smartphone camera can take a photo of your retina and tell you what is the probability of you getting diabetes. That's certified. That's a doctor's job. Scanning of X-rays, scans, for example. So computers today, neural networks can spot patterns, can spot insights which a doctor could have easily missed, which a human could have easily missed. So there are some tasks even for a doctor which can be done by AI. But again, I'm not saying doctors can be replaced. They play a very noble profession. But in our industry, we can see what type of jobs can be replaced by AI. Those are professional technologies. And then non-routine jobs like a scientist job, these are very high on decision making, very low on programmability. They will never get replaced by AI or robotics. So if you look at these 4 categories, routine jobs are at the highest risk of getting replaced by algorithms, by software, by computers, by robotics. So that's where responsible organizations should put in the extra effort to reskill these people. So that's where the human element comes. Industry 4.0 we always associate with emerging technologies, cutting edge technologies, but there is also a people aspect there. So responsible companies are already taking steps to train people. So if you look at auto industry, electric vehicles is a big trend, and they have very few moving parts compared to an internal combustion engine driven vehicle. So that's where responsible governments have already started training their people in electric vehicle manufacturing and assembly. So reskill people, move them to other types of jobs where there is employment. So that was the book. What I'm showing here is a cover for the neo-skilling book that was initially mentioned. I had the pleasure of co-authoring this book along with Professor Prasad. So that talks about the people aspect from an Industry 4.0 perspective. So these are some of the key takeaways from this session. So I covered the maturity index and how it was developed using the consortium. So in summary, it's not just about technology adoption, but reskilling is very important for Industry 4.0 to be successful, so that everybody in the society gets the benefit of it. And one more factor that most companies which got into Industry 4.0 have realized that it is not a horizontally scalable technology. It needs deep domain expertise. If I am going to implement Industry 4.0, we should ask specifically for what industry for it. It's going to vary. The flavor is going to vary from industry to industry. And oil and gas implementation is going to be very different from an automobile Industry 4.0 or a hospital, a healthcare type of implementation, for example. So domain expertise, the importance is never going to go away. So it's going to be a T type of skill sets that are available. The vertical skill sets are the deep domain knowledge that you go. There are people who have spent decades in a particular industry. Their knowledge is not going to be thrown away. It's very important to retain their knowledge. At the same time, if you look at horizontal skills, those are the technology skills that we're talking about. It could be programming in Python, it could be IoT, it could be digital twin. So Industry 4.0 needs a T type of skill set model for it to be successful. And it is business impact that's important, not just the technology part. We spoke about it. I gave you some examples where companies have benefited in the post-pandemic era by realizing business benefits from adopting Industry 4.0. And Industry 4.0 is a journey. It's not a milestone. And here we're talking about multiplicity, not singularity. So singularity is when machines can work on their own. But we are talking about multiplicity. We are talking about cobots where humans can work in collaboration with robots as colleagues. So humans will always have a role to play in Industry 4.0. So with that, I will stop my session. If there are any questions, I'll be happy to take. Let me stop sharing. So thanks once again to Professor Devraj and the organizers for giving me this opportunity to talk about Industry 4.0. Thank you so much, and I wish you all the best for the rest of the workshop.
Thank you so much, sir. Really, it was an informative session. Any questions from participant sides? You can post your questions in chat box or unmute yourself and kindly ask your questions. Thank you so much, sir. Yes, ma'am, all the recording sessions will be shared later through the email. Participants are requested to mute yourself. Sir, kindly accept this e-memento on behalf of our workshop team as a token of our love.
Thank you so much. Thank you so much. It's a pleasure to be here. Thank you.
Thank you, sir. The next session will be started 1:50. I request all participants to be active at 1:50 p.m. Thank you. I request all participants to join at 1:50 p.m. for our next session. I repeat, the next session will start at 1:50 p.m.
level 2, hands off, level 3, eye off, level 4, mind off, and then finally everything is or robot taxi in the level 5. But going forward, the safety norms is major challenge here. So to defining the safety norms and integrating a different sensors. So if you see the sensors here in level 1 and level 2, some short range radar ultrasound sensor, I will discuss later the sensor part separately. But right now, if you can see in the picture, so few sensors are involved in the level 1, level 2, but going ahead, a lot of sensors and a lot of technology and uh, connectivity is involved. So if something goes wrong in between, then definitely that is not good sign for autonomous or autopilot vehicle. And so all this should function well within their, what I can say, within their activity. Okay. The challenges, if you can see, are the perception, new sensor technology, 360 degree view, all weather condition, software defined vehicles for, like for example, a separation of software and hardware with a centralized high preference computing technology. So earlier you used to see a few issues, but the number of issues are involved are more here right now. So software complexity is again more to fuse the data coming from different sensors and actuator, and to control the vehicle is now becomes complex. For that, again, artificial intelligence is required, and deep DNN, that is deep neural networks technology is involved there. So, and again, the data driven development. So if you see, these are the some new terms where development is vastly going on. And the next thing is a vehicle network, increasing bandwidth. So as good as you are increasing number of ECUs, electronic control unit in the vehicle, so definitely you have to increase the bandwidth of the system. So for that, the new protocols are coming into the picture, like Ethernet, EtherCAT. So that will be the future. So yes, definitely. Apart from that, also we will have to go further. But right now, Ethernet and EtherCAT is sufficient to drive the AD vehicle. Safety validation and homologation. So functional safety, security, and SOTIF. So some rules and regulation we have to follow, and for the homologation, so we have to go through such a process in order to get the approvals for the ADAS AD vehicles. New testing methodologies. So testing methodologies are more right now as compared to 10-15 years back vehicle. So testing is more right now with respect to the ADAS AD. So transforming in the automotive industry transformation, if you can see the from engineering to high tech IT companies. So right now, initially in 80s, 90s, there is a very what you can say low involvement of software part in the ECU or overall in the vehicle. But however, we are moving ahead with the ADAS and new technology. So you can see the software is more important here. So the involvement of software is much higher. So that's why joint involvement is going on. Sorry, joint development is going on. So co-development between the OEMs and service provider, OEMs and service provider suppliers, more agile cross-function development within the organization, and tech native companies enter more broadly in the market, and new partnerships and new cooperations are going on. So even if you see in the uh, research organization, even in the education things, so more companies are involving or investing money for the R&D purpose. And then definitely the agile intelligence and data driven development is again the part of a challenge. So if you can see, the development, test, validation, and continuous integration and development testing will be involved. This is something the agile method right now industry is following. Okay, so the sensors involved in the ADAS. Okay, so how do the prototype looks like? So this is the reference from Daimler, Mercedes Daimler, and you can see the different sensors how can be attached while testing the vehicle. So right now it is under development. So it's definitely this is the AD vehicle, not ADAS vehicle. So the first sensor is LiDAR. So if you can see the position of LiDAR here, 1, 2, 3, 4, 5. So even more they can also include based on their data requirement. Camera, so 1, 2, 3, 4, 5. Right now they have shown 5 cameras, but nevertheless you will get more cameras. At the back side also you will get one more camera, and yeah, on the mirror. So if you can see here also sometimes we get the additional camera for the blind spot detection. When it comes to radar, so radar is again you see right now they have shown 4 radars, 1, 2, 3 at front side, and fourth is at the right side of the vehicle, or if you are looking from the front it's left side of the vehicle. Similar to that, at the right side of the vehicle there's one more, and 2 corner radars at here, like one is at the back end corner, right and left, and backside radar. So overall 7 to 8 radars will be involved in the AD vehicle. So to get this, again one more sensor, the ultrasound sensor. So this is the normal sensor. Right now we will find it in almost every vehicle for the park assist at the back side and at the front side. This is generally located on the front bumper and back bumper, and these all sensors are playing major roles. So whenever they are getting data, and that data is in a huge format or bandwidth is huge, so we have to fuse this data. We need a central controller to manage this data, and some algorithm has to work on this, and after that fusing this data, so we have to act accordingly on the road. So that is what the major challenge right now. Nevertheless, the bus systems or the communication systems are right now used for different sensors, definitely the interfaces with respect to each and every sensors. So I will give some example. Generally for LiDAR sensor, we use Ethernet communication. So it should be 1 gigabit Ethernet or 10 gigabit Ethernet. So because the LiDAR has more point cloud data, and yes definitely it is collecting more information other apart from, like if you take example with respect to other sensors like camera, ultrasound and radar, so the data rate which is more. And in case of radar, just CAN-FT is involved, sometimes flex ray, and the camera generally works on USB serial communication and sometimes Ethernet also. So based on the camera type, we have a lot of camera sensor manufacturer in the globe. So based on their interface and based on their camera type, so that camera can be used. So what is the main challenge, or what is the thing here we are looking for in the ADAS? So high bandwidth, definitely. So when it comes to all the sensors, high bandwidth is involved. Flexibility and scalability is the key process, and all the logs has to be collected synchronously. Okay, log all the data. And there's one more challenge while developing this kind of ADAS, we need a data logger also. So data logger is one of the key product here, which right now most of the OEMs and what you can say tier 1 companies are looking for or working on it. Okay, how do we support? So how do we support in the sense all the sensors and involvement of a different technologies, how we can test? So option 1 is a rest bus simulation. So this is your HL simulator or hardware in loop simulator generally in layman language. And the option 2, insert object list. Second method, option 3 is insert raw data after recording the data. And third is option 4, the over the air simulation. And the sensors involved here, if you can see, the camera, radar, lidar, ultrasound, GNSS, okay, GPS sensor, V2X, vehicle to vehicle, vehicle to infrastructure communication, V2X, LTE, okay, there are different type, and electronic horizon, okay. So this much things are involved as far as you go for autonomous or ADAS vehicles. Okay, so back in what you can say 10 years back, I can say, or right now, what is the situation before 2-3 years, uh, or for the ADAS vehicles. So the number of ECUs involved are less, but right now, if you can see, the ECUs are increasing. This is the situation for most of the volume OEMs, those who are entered into right now in the ADAS. So there is a steering issue, braking issue, engine, and transmission. These are the traditional issues where all the things are like coming from our uh, recent past. Okay. On top of that, when it comes to ADAS, so front camera, front radar, surround and rear view camera, ultrasound sensor, and side and rear radar. So how this can be used? Front camera basically used for uh, LWD, TSR, and vulnerable road user detection. ACC, adaptive cruise control, front radar can be used, and autonomous emergency braking. The surround view camera and ultrasound cameras will be used for automatic park assistance. And then the side radar or corner radar basically used for blind spot detection. And definitely then map and GNSS will help you to predict the traffic conditions and all. Okay. Okay, so addition to that, when it comes to AD, okay, the premium vehicles or the vehicles which are mainly involved in the AD development. So they are managing their systems like this for ADAS and AD. So if you can see, the system looks like same, how the major OEMs are taking care, but uh, there are some things they are taking as additional. There is a additional redundant issue or redundant system for the steering. For braking also, there is an additional redundant system, because as they are going for ADAS functionality, so they have to rely on another if as a fallback system. Okay, so if you see, the sensors are more or less similar. So front camera, front radar, surround view cameras, ultrasound sensor, and corner radars. But the system is again integrated with technical feedback, that is application function, one more controller that will do the fusion of all the sensor data. Okay, so that fusion is happening here in between, and then they are exchanging the data, and finally that data is going to control all the things. Okay, so that again fallback system is involved in the central control system, which is taking care all the sensor data coming from these issues. Okay. Okay, so finally, when it comes to the our portfolio, so data logging. So maybe just a moment. So okay, so when it comes to ADAS and autonomous driving, so DSpace provides end-to-end solution, but right now the major challenge right now OEMs and the tier one suppliers are facing. So they have to integrate a lot of things and they have to work on that. But DSpace is providing end-to-end solution. This is something we are providing as an end-to-end solution while developing the ADAS and AD. So starting from the data logging. So
00082.
data logging is a robust in-vehicle data logging system with outstanding performance of recording the sensor raw data. So I was explaining in the previous slide. So data recording is one of the major challenge right now, which OEMs are facing. So they need more storage capacity for the data logging. So in that lines, we have a product called as Otera. So in that we are providing data logging solution. The next is machine learning. So the machine learning is involved data analysis and data process. So once you record the data, so the machine learning after the data recording is involved here. The next is in-vehicle prototyping. So once you done with data recording on all these things and in-vehicle prototyping, this is one of the thing which you can do the vehicle testing by keeping your controllers in the vehicle. So using existing data as well as with respect to the different controllers. Okay. The data enrichment. So the data enrichment is nothing but the recorded data can be annotated. So the meaning here is data selection, anonymization, and annotation with the best class quality through the automation work. So DSpace acquired recently understand AI, and they are working for the data enrichment through different AI algorithms. So production software development. So modeling with high quality code generation, verification, which is compliance with AutoSAR, and classic adaptive AutoSAR with the different platforms. Okay, so that is also there. Data replay. So the recorded data can be replay with the time synchronous manner. So the sensor raw data and vehicle bus data can be replay time synchronously with this tool chain. The vehicle environment and the sensor simulation. So basically, if you can see the vehicle environment and sensor simulation, this involves highly realistic simulation. So maybe after this slide, I will show you one simulation tool called as Aurelian, where you can see how the simulation is done through the 3D animation. So that involves here and SIL testing. So in the SIL testing, powerful PC or cloud-based simulation is involved. And in the hill testing, real-time testing with the real hardware is involved. So this is again the part of the vehicle environment and sensor simulation. On top of that, you can go ahead with hardware as well as software. Scenario generation. So this is something new solution or new era, what you can say, product. So scenario generation, so automatic generation of simulated scenarios from the recorded data. So for example, if you have a sensors like radar, lidar, camera, and you are recording the real-time data from the road, and that recorded data can be converted into synthetic scenario using this kind of a scenario generation tool. And now the scenario based testing. So scenario based testing is nothing but validating software for autonomous driving by automatically performing and evolving millions of test cases. So for example, right now for the ADAS and AD, we have to do a lot of series sorry, power cutoff issue. So maybe I'll just hope I'm audible. I'm just sharing screen again. Okay, I'm audible.
Yes, sir.
Yeah, great. Thank you. So, uh, yeah, where I was like scenario-based testing, the validation software and autonomous for the autonomous driving automatically. So for the series of testing, so millions of test cases are involved. So that's why we are introduced the scenario-based testing, and where different automation tools are involved in this product line. And the data and test management. So again, this is the part of the series testing. So in that, generally we do the central management and measurement for the simulation and test data, connectivity testing, end-to-end solution for the testing V2X and cloud-based service for the connected vehicles. Finally, the end of line sensor testing. So end of line sensor testing, and there's one more periodic testing is involved. So end of line sensor testing is precisely, we can say, uh, the solution is cost effective, high throughput, and the end of line testing basically in the production we do support on those lines also. So if you talk about each and every segment, we have a detailed solution. If a customer is working on the different zone of ADAS. So yes, definitely we are providing all the solutions to customer on the all product lines here. Okay, so finally, I will end up my session with one of the video. Let me see this. Okay. So this is one of the product called as Aurelian, and how the 3D environment is created. You can see in the Aurelian. It's a testing environment where the plan model from the MATLAB side is involved, and different sensors are also integrated with the vehicle. So such kind of vehicle you can create or you can insert in the scenario, and you can start testing with the different weather conditions like this, and different scenarios like the ADAS testings like ACC, AEB, and other stuff. So this becomes a more realistic, if you can see. Right now, definitely it's the scene more towards the European scene, but as it can be modified based on the region wise or country wise the environment, and you can create different scenes. The night vision, and you can create a different environment condition, and if you can see the light effects, okay, with respect to weather, that can also be created. So this is one of the example of NCAP testing. Yeah. Yeah, so such kind of environment you can create. So city view and yeah, different views, and you can start working on the different ADAS feature testing. Okay, great. So thank you for listening, and thank you for joining the session. So if I think I'm done from my end. So if you have any question, we can take for the next 5 or 10 minutes, whatever the time remaining here. Thank you. Thank you all.
Thank you, sir. Sir, can you stop your screen sharing option, sir?
Yeah.
Thank you, sir.
Yeah. Thank you.
Participants, can you ask your questions? If you have any doubts, you can unmute yourself and ask your question. Any physical participants? Sir, that is a question. Is there any simulation tool available for together, like physical system, communicating system to work together in a simple simulation, sir?
Yeah, we do have a simulation tool called as on display side, and that is, we call it as ASM simulation. So you can go through our DSpace website, and there is a provision to integrate different sensors on the ground truth site. Yes.
Thank you, sir. Sir, can we accept this e-memento on behalf of our IEEE branch as a token of our love? Thank you for your valuable and informative session, sir. Our next speaker is Mr. Shiva Kumar. Mr. Shiva Kumar received his master degree under Power Electronics and Drive specialization with power converter control for motor drive and renewable energy applications being his play zone. He is currently working as a field application engineer in Opel RT Technologies, Bangalore. He is actively involved in FPGA firmware development for customers across the world and providing technical support on and off customer sites in India for working with our real-time digital simulators. The session will start with the fundamentals of real-time simulation, followed by an overview on how to make a simulink model to interact with the external world will be discussed. Finally, a live demo of rapid control prototyping simulation for a voltage and frequency controlled induction motor drive will be shown. Yes, we welcome you, sir.
Hi, good afternoon all. Thanks for the warm welcome. Well, I think I can, without wasting much time, I can start sharing my screen and I'll show you the PPT maybe. So is my screen visible? Can anybody just confirm it once?
Yes, sir. Your screen is visible.
Okay. So yeah, again, good afternoon all. Still, since we have just maybe I was assigned just 1 hour for this session. So I will try to cover max, and I'll try to share some of my knowledge on real times. I think I need to close this maybe. Oh, fine. Okay. So I will try to share max of whatever knowledge I have gained so far on my experience with Opal RT. So it will be like based on real-time simulations, and these are all the things which will be discussed. We will start with the fundamentals of real-time simulation. What is a real-time simulation? Why do we need it? Where do we need it? Those kind of stuff. And after that, how do we make a Simulink model to interact with the external world using an OP4510 real-time simulator? OP4510 real-time simulator is one of the most selling products of Opal RT Technologies. So I will be trying to give some overview on this hardware, and I'll tell you how to make your Simulink model to interact with the external world. Finally, I will be showing a live demo of V/F controlled induction motor drive. We have a hardware setup right in front of me in the lab here. So yeah, so we will start with I'll just start with a company introduction, who we are, what we do, and where are we. So many of us might know who are Opal RT. So Opal RT is a world leader in development of real-time digital simulators. They find applications in rapid control prototyping and hardware-in-loop based simulations. Also, our products find are widely used in electrical domain for simulating power electronics and power system based test benches, and we find applications in aerospace and defense kind of fields. Like we have some government organizations who are working under or working with our simulators for aerospace and defense. And obviously, like if even we are into the automotive domain, as we all know, electric vehicle is booming in the market. So our digital simulators find applications in automotive sectors. Also, most of the academic and research institutions are working with our simulators to test their projects and stuff. And we have other industries also who are actively working. It was founded in 1997, and we are located worldwide. Actually, Opal RT products various kind of Opal RT manufactures various kind of products, starting from very basic simulators to more powerful, flexible, and scalable simulators. Like they are compact and portable devices, and also we manufacture big integrated HIL test benches, which are more powerful, flexible, and scalable. So we are worldwide, as I told earlier, and we are headquartered in Montreal, Canada. In India, we are located at Bangalore. So Bangalore office takes care of the support and sales of our real-time digital simulators throughout the country. Also, we support Montreal also parallelly. Fine. Okay, I'll start with like the benefits of simulation. Like we are speaking about real-time simulation. So we are working with simulation. So why do we need to simulate? What is the basic need to do the simulation? In order to explain that, I would like to stress upon what are all the different stages in which an engineer will go through while working with a project. So he will start with the basic design. After that, he will proceed to the coding and implementation part. After that, he might perform some integration tests and system tests to make sure that the idea or the implementation is working fine or not. Finally, he will reach the delivery stage where he can deliver his product. So the thing to note down here is that engineer might face any kind of errors in any stage of this process. So the thing is, he needs to find that error as early as possible. Why? Because as we can see, the more he delays to find the error in his product or in his approach, the cost to fix that error will be increasing. So it is always recommended, or it is always aimed to find the error in his idea at the earliest stage possible, that is the design stage, so that the cost to fix that error is minimal. So that is where simulation finds its major advantage or application. Simulation helps us to find the error in your idea or your project at the design stage itself, so that the cost to fix that error is minimal. So this is one of the most important benefit of simulation, and I hope it was clear. And there are some more benefits of simulation. We might face some challenges in working with an research idea or projects. For example, we might have to work with expensive hardware, or we might have to work with highly complex logistics and circuitries which are difficult to handle. And sometimes we might also work with some hazardous equipments also. So these challenges are tackled by simulation tools. Simulation tools helps us to do verifications all along the project. Also, yeah, as I explained in the previous slide, early detection of errors is possible, and we can do infinite test capabilities using simulations in a more easier way. And it helps us to reduce cost in the sense I am speaking about the cost which is reduced while we are trying to rectify the error. So that is why we feel simulation helps us to reduce the cost of the project. It helps us to reduce the delay in delivering your project. Why? Because we can independently develop the hardware and software of the controller in which we are working on. I will explain you this point in the next slides, how simulation helps us to reduce the delay in delivering the projects. And obviously it helps us to reduce the risk in working, because we can test our systems for adverse quality conditions, because we know that working with fault scenarios or performing fault-based tests might be hazardous, because it will involve more current and voltage ratings. So again, simulation helps us to reduce the risk in which we are working on. I think I would request some of you to mute your mic if you are not speaking. If you want to raise a query, or if you have any questions, you are free to unmute your mic and speak. But if you don't have anything to speak, I request every one of you to mute your mics. Yeah, now it's fine. Thank you so much for the understanding. Now, I have something to explain about model-based design. What is a model-based design? Opolarity, like in our company, we follow a model-based design approach to give simulation solutions. So what is a model-based design approach? So we work with simulation models. Like we might have some control algorithms which is modeled in a simulation platform, or we might have some physical models of an electric vehicle or a car based simulation. We might have a physical model in a simulation based environment, or we might have some complex power system based model in a simulation environment. And also we might have some M files or codes which needs to be worked. So it is like we work with models, we work with simulation models. So whatever might be the model, depending on the application, we will build that model onto our real-time simulator, which is manufactured by us. So it is a model based design. We start with a simulation model and we will try to execute that model onto the real-time simulator. So we start with the design of the model. After successfully finishing the design of the model, we will proceed with executing our model onto the real-time simulator. And after making sure that the execution on real-time simulator is fine, we will try to introduce our simulation to the external world to do some hardware in loop based testing. And if we feel the results are not fine, then we will again go back to the design of the model, make some changes, again execute on real-time simulator and test it in hardware in loop. So yeah, this is how the workflow in which Opolarity follows. And also we have various stages of verification before or not before, while implementing a project. Like if you have an idea or a research idea, we can't directly or blindly work with a real hardware setup. We need to follow a step-by-step verification process in order to implement your idea in a complete real hardware setup. So in those steps of verification, the first stage of verification is the model in loop. Model in loop means the idea or the project will have a controller and plant. Both the controller and plant will be running inside our real-time simulator. It is just an acceleration of the simulation. We won't need any IOs or input-output channels to be configured for this model in loop based verification. It is just an acceleration of the simulation, and we will just verify whether the controller and the plant are working fine in a real-time scenario. After verifying our model, we will proceed with introducing our, or we will proceed with slowly introducing our simulation model to the external world. And that is where rapid control prototyping comes into picture. In rapid control prototyping, we will have a real plant in the external world, and we will have the controller inside simulation. This will help us to rapidly prototype our control algorithm, and we will see how the control algorithm behaves with a real life dynamics or a real hardware. So depending on the behavior of the real hardware, we will be able to rapidly tune this controller in an easier way. After making sure that the control algorithm is fine, we will just proceed with the hardware in loop based setup, where the controller will come out and the plant will be simulated. We will see how our control algorithm behaves in a real microcontroller or some other controller. So we will have a real controller in the external environment, and we will try to test that real controller with a simulated plant, so that we might need, or we might know what are all the changes are needed to be done to our plant to make it compatible to the controller. So this is an hardware in loop based verification. So after making sure that our idea works fine with model in loop, rapid control prototyping, and hardware in loop, then we will go with the real implementation in a complete hardware setup. So that is why I told one of the benefits of simulation is it helps us to verify both of your hardware and software independently, so that it will help us to finish your project with reduced delay. So that is what I told. Simulation helps us to reduce the delay of our work. And we have one more thing called as power hardware in loop. I think this thing is hiding the title of my slide, but I don't know how to close this thing. You have to kindly bear with this. So anyhow, I'm telling the title. So it is we have something called as power hardware in loop. Power hardware in loop is a case of hardware in loop where we will have a power amplifier between our plant and the simulator. Why? Because the simulator of O-polarity will have its own limitations pertaining to the voltage ratings. Our simulator, the output voltage rating of the simulator is just plus or minus 16 volt. Whereas if you are trying to work with a real microgrid, which will be on the order of kVs, then in that kind of a scenario, we need to have a power amplifier in between. So again, this power amplifier will demand some modifications which needs to be made in this simulator. Those are some advanced concepts, but just try to understand that we have one more stage of verification called power hardware in loop, which involves a power amplifier between the simulator and the real plant setup. So I'll tell you what is exactly a real-time simulation. Like, we have understood what is the basic workflow of O-polarity, what is the basic workflow in which O-polarity follows. And after that, we are speaking about real-time simulations. Real-time simulations are something different than the normal offline simulations in which we do using MATLAB, for example. So how is a real-time simulation different from an offline simulation? So in a real-time simulation, real-time simulation means it has to give good result, obviously, but it has to give the result at the right time. So what do we mean by a right time is, well, to make it simple, real-time simulation means the model's execution time has to follow a real clock. So does that mean real-time simulation is very fast? No, actually there is a famous misnomer like real-time simulation means they are very fast simulations. No, it is not necessarily very fast. Real-time simulation means it is fast enough. Fast enough means it is fast enough depending on the application, because some simulations might demand to work with sample time of microseconds. For example, if we are trying to work with electromagnetic transients, then it will demand time steps of the order of microseconds. If it is microsecond, it has to be in microsecond. It should be in real time. It has to follow the real world clock. So that is where I'm saying real-time simulation means it should give the result at the right time. But it doesn't mean that it is very fast. It is fast enough depending on the application in which you are working on, or the simulation model in which you are modeling. So maybe this slide will help you to understand what is exactly a real-time simulation. So we have a real clock here, which is ticking. We can see that offline simulations will not follow this real clock, whereas real-time simulations will follow this real clock. And also real-time simulation, there should be a sync between the real clock and the simulation's execution time. So that is what is real time all about. So when do we need, why do we need real time, and when do we need real time simulation? So whenever we are trying to work with a real hardware connected to the simulation, we will need real time. Why? Because we can consider a power system based scenario where we have a circuit breaker which needs to be opened at 4 seconds. So in this kind of a scenario, even though if you open that circuit breaker at 3 seconds, it will be wrong. And also if you open the circuit breaker at 5 seconds, it will be wrong. So if it is 4 seconds, then it has to be 4 seconds. So whenever you are trying to work with the real hardware, real time is needed. So that is why I am stressing about this this like about the simulation needs to follow a real clock. Also, we follow determinism in real-time simulation. Determinism in the sense, as I explained earlier, we are deterministic that our simulation has to follow this fixed time step. So that is why we say real-time simulation are deterministic. Like, yeah, it will be like a repeat of the slides. Why? Because I just wanted to hit the nail on what is exactly a real-time simulation. So we will have a controller and we will have a plant. So if we are trying to implement in real time, this controller needs to send the signals to the plant at the right time specified. So that is what is real time all about. So maybe to give more idea on real time, like every simulation will undergo 3 steps. It might do some measurements, it will do some computations, and it will give some comments depending on the computation. So all these things should happen at the fixed time. So if it is if the fixed time, it is, for example, if the computation is not happening in fixed time, then we coin a term called as overruns. So if there are any overruns, we call it as like real time is not respected. So we need to make sure that we are working with 0 overruns in real time simulations. And these are some of the hardwares provided by Opolarity. And I would just quickly explain the hardware setup. How will the hardware setup of Opolarity look like? We will have a host PC where we will have the simulation model, and we will have a real-time simulator where the simulation model will be executed, and also we will be doing some IO management. So these two, host PC and the real-time simulator, will be communicating through an Ethernet or TCP/IP link. And also this simulator has a multi-core CPU, which helps us to execute all the models in real time. And also the simulator has an FPGA, which helps us to make the simulation to interact with the external world. And we have some software packages delivered by Opolarity, depending on what kind of application in which you're working on, and on which or what kind of time step in which you need to work on. And also depending on the complexity of the circuit or the complexity of the model in which you are developing, and also the time step in which the model is going to be executed on. Opolarity gives a lot of software packages which are linked to MATLAB. For example, this eFPGA sim is especially for power electronic simulation, which needs to be simulated in the nanosecond range. For high switching frequency application, we go with this eFPGA sim software package, which is linked to MATLAB Simulink. The same way, we have eMegaSim and ePhaserSim for power system based simulation. Depending on the number of nodes in your network, you can choose between eMegaSim and ePhaserSim. And again, we have one more package called HyperSim, which is outside MATLAB Simulink. It is a separate software given by Opolarity, especially for power system based simulations. So now I will give an introduction on the hardware and how to configure the IOs, or how to make a simulation model to interact with the external world. So yeah, like these are the three most products manufactured by most famous products manufactured by OpenLRT. O4510 is a very basic, compact and portable simulator. 5600 and 5700 are more advanced simulator, which comes with more CPU cores so that you can work with more complex models. Like I will be concentrating on this 4510 alone. So this 4510 comes with 16 analog and 16 analog out and analog in channels and 32 digital channels. Also, it has some optical interfaces in the front side, which helps us to do some communication with other devices. And 4510 comes with an Kintex 7 FPGA. Kintex 7 FPGA is an FPGA manufactured by Xilinx. I hope we are aware of that. And this is just a blasted view of our simulator. How does it look inside? Here we have, in the top side of the simulator, we have the IO boards, the analog and digital input and output boards, which helps us to introduce your simulation to the external world. And the bottom side of the simulator is equipped with the processor and CPU, which helps us to execute your simulation in real time. This is an overview of the Kintex 7 FPGA, which is embedded inside the 4510 simulator. It can connect up to 4 swappable IO boards. It can be either digital or analog. And also it can simulate power electronic simulations in nanosecond range with the help of the eFPGA software package provided by OpenLRT. And Kintex 7 FPGA is highly flexible also. We can go for different IO combinations. And next is the OP5600. The difference between 5600 and 4510 is 5600 comes with more number of CPU cores, and it comes with a more advanced FPGA called Vertex 6 FPGA, and it supports more number of analog and digital IO connections. Like 4510 had only 4 IO boards, but 5600 comes with 8 IO boards supporting up to 128 analog input outputs and 256 digital input and outputs. This is just the exploded view of 5600. Again, it has the IO boards in the top section, and it has the real-time multi-core CPU in the bottom section, and it has the FPGA in between both, which helps us to synchronize the IO boards with the CPU. This is an overview of the Vertex 6 FPGA, but I think the current simulator has an even more advanced FPGA. It is a Vertex 7, and it is even more accurate and flexible to work with simulations on the order of nanoseconds. Like these are the IO modules which is present in the top section of the simulator. We will have these cards embedded into it, and the customer is free to choose what kind of card does he need. I will discuss like what are all the different types of analog and digital cards are available with OpenLRT. So basically, the analog output and analog input, there is a voltage range for the analog output and analog input. So it is analog outputs are limited to just plus or minus 16 volt, and it has a conversion time of 1 microsecond. And it's like there, I would like to show you. I would encourage every one of you to go into the OpenLRT's website and check what are all the IO cards manufactured by OpenLRT. I can just quickly show you this. Yeah, under products and services, and we have these IO and communication interfaces here. Yeah, so these are all the different types of analog out and analog input cards manufactured by OpenLRT. For example, if you see this OP5330, it is an analog output card which works at a sample time of 1 ms per second. If you want to get more details of this card, you can go into it and you can see what is the voltage rating, what is its calibration, up to how much frequency it can handle. All those details will be given here. Maybe I can quickly show you that also. Yeah, here we go. Here you will be able to see how this OP5330 or what is this card capable of. What is the voltage rating? What is the current limitation? What is its sampling rate? What is its resolution? And depending on all these parameters, there are different types of cards available. As you can see here, we have analog output itself. We have different types of cards. Here you can see we have 5330, 5332, and in the same way we have different analog input cards, and also we have different digital out and digital in cards depending on what voltage rating you want, what current rating you want, and what sampling rate you want. So that is what, so customer can choose what type of analog card or digital card he needs for his kind of application, and he can purchase the simulator. So I will just switch over to the PPT. Yeah, in the same way, we have the digital input and digital output cards with 32 digital in and digital out can be connected in each slots of the simulator. And these are all the current ratings and voltage, and you will be able to get the details of the digital or the various types of digital out and digital in the same link which I shared you now. Maybe I can put that link in the chat box also. Like at the end of the meeting, I'll just do that. And also, we like before what to say, before trying to make your simulation to interact with the external world, we need to understand how the simulator is set up, or how it is arranged, or how it is connected, or what is the pin configurations. In which slot do we have the analog out? In which slot do we have the analog in? Where is digital in? Where is digital out? All these informations needs to be understood clearly before we try to make our simulation to interact with the external world. So that information you can get in the system description document, which will be delivered to the customer when they purchase. Here you can see in this diagram, we can see that where the analog out and analog in, digital out are situated. I can explain you by showing the hardware setup which I have right in front of me. Like while showing the live demo of the induction motor drive, you will be able to understand what I'm speaking about. So okay, now how do we configure the IO cards? That is the next question. How do I send a signal to analog out, or how do we send a signal from my simulation model to digital out? So all these things needs to be clarified. So for that, I would like to show the hardware setup, or how the hardware looks like exactly. Again, I would like to shift to this another open source documentation available in OpenLRT website. I think my mouse is not responding. Let me just check here. Yeah, here we go. Here we have here we have this OP4510 which I spoke about. How this looks like, or how do we understand where is analog out and where is analog in? So I would like to show the rear interface of our simulator, where you will have like these analog and digital slots. We need to understand which is what. This complete IO setup is divided into groups, slots, and sorry, it is divided into groups, sections, and subsections. Like how to say is, like for example, here we have 1A. 1A means, what do we mean is, it is it is slot 1 and group A. So depending on whether the IO board is an analog or digital, we divide it into 2 slots. Slot 1 is analog and slot 2 is digital. And depending on whether it is an input or output, we divide it into groups. That is whether if it is group A, it is an input, and if it is group B, it is an output. And also we will again further divide the group into subsections. For example, if I say 1A, it is analog out. So analog out will have 16 channels. So we will divide it into 2 subsections for an easier workflow. So yeah, so what I need to explain is we need to understand how the simulator, where is the analog out and digital out cards are placed in the simulator. We need to understand that. So we need some terminologies for that. So what is a group, what is a slot, and what is a subsection? So that is what I felt like explaining. And that is also, you can go through this open source documentation which is available here to understand what is this groups and what is this slots and what is these subsections. So again, I'll continue to this PPT. So if I say like slot 2B1, it means it belongs to slot 2 module B and subsection 1. That means 2B means it has to be digital out as it is shown here. So maybe it might seem to be confusing when you see it for the first time. But when you work more with these products, you will be able to understand what are these terminologies are. You will get more used to it. So as for now, we need to understand that 2B1 means it is digital out, or if it is 1A1, it means analog, like that. Again, the system description document will explain all these stuffs. So as soon as the software packages provided by Opolarity is installed, we have specialized blocks in MATLAB library, which helps us to send your signal to the external world. For example, depending on the analog signal or digital signal, you can select those blocks and you can send your signals to the channels in which you are trying to configure. So Simulink IO blocks are available for analog and digital signals. So also we need to give a firmware for the FPGA in order to configure the IO blocks. So we will have something called as the OP control block, which helps us to add your firmware file, FPGA's firmware file onto the simulation. So what is this firmware file? Why do we need this FPGA firmware file? Is like your simulator will have the IO configurations. The IO configuration of the simulator will vary depending on the customer's requirement. So what Opolarity does is it gives a firmware to the FPGA, or it gives a firmware to the customer when the product is delivered. So that firmware will make your simulator to understand where is the analog out and where is the digital out, or where is digital in, where is digital out, where is analog in, where is analog out. Those kind of things will be done by the FPGA firmware. So this firmware file is highly needed, and it is custom generated depending on the need of the customer. So we need to provide this FPGA firmware file in order to make your simulator to interact with the external world. I will quickly show you one model of this. I will quickly show you the live demo of the induction motor drive so that you will be able to understand what is that firmware and where to place it, how to configure the IO cards, everything will be clear. So yeah, we need to have that OP control block in our simulation model, and after placing the OP control block, we will add all the input-output blocks which will be available in your Simulink library. So we will have the analog in block, we will have analog out block, And we need to configure these analog in and analog out blocks in MATLAB environment. We need to provide some data import numbers and how many analog out channels are required. All these things can be configured in MATLAB Simulink. I will show you the Simulink model and I will explain you, and you'll be able to understand even more clear. Rather than explaining these things in the PPT, showing a model will be even more straightforward and clear. So like again, if it is an analog signal, like whenever you are trying to make your Simulink model to interact with the external world, depending on the type of signal, the type of signal in which you are sending it to the external world can differ. It can be either analog or digital. If it is analog, it is straightforward. It is going to be just analog in and analog out. But if it comes to a digital signal, we have different types of digital signals. We can work with static digital signals, or we can work with pulse width modulated digital signals to control power electronic components. Or we may also have some timestamp digital signals, like timestamp digital signal in the sense it is an even more an advanced digital signal with high switching frequency. That's what I can say. So timestamped, PWM, and static are the three types of digital signals, and OpenRT provides different blocks to configure these types of digital signals. Yeah, just to give the differences between all the three types of digital signals. Static means it is just the logic state can be changed only once per time step. You can see the example here. If it is a PWM signal, both the frequency and duty ratio can be changed once per time step. If it is time stamped, like the change of the frequency in duty ratio will be even more complex, or it will be even more than a PWM signal. Like it is a higher switching frequency signal, we can say, where both the duty ratio and frequency will be changing at each time step. So I'll show you how to configure all these signals in OpenRT. Yeah, again, we have a separate block for digital in, digital out, and PWM in, PWM out. I would like to explain one more thing here. We have something called as port numbers in each of the blocks. I will explain these port numbers while showing you the model. Also for timestamp digital signals, we have this event detector and event generator blocks, because since timestamp signals are with high switching frequency, we have a separate block for that. And also we have one more library or one more block set called RT events, which helps us to generate timestamped digital signals. So what is that RT event block is all about? It is like the digital signal will be or it will be designated with states and times. It will not be designated with frequency and duty ratio like what we do with PWM signals. The digital signals will be designated with state and time. So the signal, the digital signal is highly complex, or it is working with a more switching frequency in such a way that you can't define a fixed frequency and a fixed duty ratio to that particular signal. In that kind of a scenario, we designate that digital signal through states and times, like at what time what is the state of the signal. So this will help us to generate digital signals with varying duty ratio and varying switching frequency. So we have a separate RT events block sets in Simulink, which will help you to generate this timestamp digital signals. Yeah. Now I will quickly show you the simulation model of the induction motor drive, and I will show you how am I trying to control a real induction motor and an inverter, which I have at the lab right now through the OP4510 simulator. So I will shift to this MATLAB screen and I'll show you this model first. Yeah. So, like whenever we are working with real-time simulations, the top level of your simulation model should have only subsystems. So that is why we have one SN subsystem called the subsystem master, and we have SC subsystem called subsystem console. So this master subsystem will have all the computations happening for your simulator, and this console subsystem will have the access to the control variables of your plant. First, I'll get into this console subsystem. Why we are dividing it into two is, so this master subsystem will be executing into our simulator, and the console subsystem will be executing in the host PC, so that you will be able to access the results of the model which is being executed into your simulator. So all the results of the model which is being executed in the simulator will be viewed in this console subsystem. And also all the control variables of your simulation will be given to this console subsystem, so that you have access to it through the host PC itself to control the simulation which is running inside your simulator. So I'll go into this console subsystem and I'll tell you what are all. So here you can see we are in this console subsystem, we have the speed of the actual speed of the motor which will be running in the external world, and we will have some monitoring of the simulation, and we have all the voltage signal, current signal, the gating pulses which is being sent out, everything, all those access we have in this console subsystem. And also we have access to the control variables. We need to give the reference speed of your I am getting a pop-up here. I think we have to close it. Yeah, now it's fine. Also, yeah, we have, other than the visualization of the results, we also have access to the control variables. Here we are giving the reference speed for the induction motor, which is going to be spinning in this lab. And also we have access to enable closed loop operation here. And also we have an option to enable the switching pulses, and we have the option to give the switching frequency of your gating pulses, which is going to be sent to the real inverter which you have in the lab. So this is what this console subsystem is all about. Next is this master subsystem. So in this master subsystem, we will have all the IO configurations, like where should I send my gating signals, to which slot should I send my gating signals, and how will I get my speed signal feedback, from which slot will I get my speed signal feedback. All these things will be configured in this master subsystem, and also the control strategy of the induction motor will be modeled in this master subsystem. So as I told earlier, we have something called as this OP control block. This OP control block helps us to add the FPGA's firmware as we have here. This .bin file is the FPGA firmware file, which will be delivered to the customer when they purchase the simulator. This firmware file will tell you what are all the slots available in the simulator and what type of slot it is, whether it is an analog or whether it is a digital, or whether it is an input or whether it is an output. So that is why we add this firmware file in this OP control block. After adding the firmware file, we will get the switching frequency and the modulating frequency thing from the reference speed from the console subsystem. Depending on that, we just have a simple PI controller which compares the actual speed and the measured speed of the simulator, and it will give the duty ratio command to this PWM generator which we have here. This is a special special block which comes along with the Opal RT Simulink block sets. This block helps us to generate the gating pulses depending on the switching frequency and duty ratio in which you mentioned. So since it is an inverter, we need to give a sinusoidally varying duty ratio. So that is what is happening here. We get the duty ratio command from this PI controller depending on the error between the reference speed and actual speed. That duty ratio command is generated like in a sinusoidal fashion, and it is sent to this beam generator. So now here we will get all the gating pulses. So these gating pulses will be sent to this will be sent to the IO interfaces which we have here. As I told earlier, since induction motor drive will have a variable frequency and a variable duty ratio for in the gating pulses, we need to have a timestamped digital output. So that is why we have this event generator here. Again, this RT events block sets will this block set provided by Opolarity will help you to convert your digital signal into states and time format, and those states and times are given to this event generator. And here you can see that these signals which you have here are being sent to slot 1B2. That means it is being sent to the digital out of the simulator which you have here. I'll tell you what is this slot 1B2, and I will show you that slot in the video right away. How do we make sure that these signals are sent to this particular slot is the next question. So we need to do some configurations here. This port number, this data in port number helps us to assign to which particular slot do you want me to send the this digital signal. This port number is like it depends on the FPGA firmware. You will be able to understand if you see that firmware, and our engineers will train you on how to assign these port numbers whenever you purchase this simulator. So I'm skipping it right away since because of short of time. Just understand that this port number will help us to assign like where to send these digital signals. That's it. And in the same way, we have an event detector here because we need to sense the encoder signals so that we get the speed, actual speed of the motor. So we are getting the encoder signals. We are connecting the encoder signals to 1A1. That is a 1A1 slot of the simulator. I'll show you the connection setup quickly. So from there, we are getting these encoder signals here. And from the encoder signals, we are getting the frequency information of the encoder signals. And that frequency information is calculated to get the actual speed here to do the control. So that's it. So this is what I felt like explaining you in the model. And also we have some analog inputs, like we are getting some current feedback from our from the inverter, and we are just trying to feed it to some grids and those kind of, like, this is like out of scope for now. This we developed for more understanding on what is happening. So right now we need to concentrate just on this induction motor control which we have here. This part we can ignore as for now. Like I'll just show you the connection setup corresponding to this Simulink model. And I would also like to explain you this special RT lab block which we have here. We have this OPCOM block. This OPCOM block helps us to establish the communication between the host PC and simulator. So all simulation model which is being executed in OpenRT simulators will have these OPCOM blocks. And also we have one more block which helps us to monitor the simulation. Like what is the computation time? What is the step size? Are there any idle times for the simulator? What are the number of overruns which is happening in the simulator? All these things can be monitored. That is why we have this monitor block. So having been explained the model, I will just quickly show you the connection setup here. I will start the execution of this model quickly. So in order to execute this model into our real-time simulator, we have a special software called as RT Lab. this RT lab helps us to build this Simulink model, which we have right here, onto our real-time simulator. So in RT lab, we need to import that particular model here, and we need to load that model with the option which we have here. So I'm loading this model now. Let it get loaded. So like while loading, what we need to understand is the firmware file which I told, as I told, the FPGA inside our simulator is equipped with a firmware or bitstream. That is the most important step which will happen during this loading process. Here you can see that the simulator is, or the host PC is trying to flash the FPGA bitstream which we have selected. So you can see that the bitstream has been successfully programmed so that the simulator will understand that I need to send all the signals or all the gating pulses to these particular slots. So that is what I would like to stress upon. And I will execute the model now. If I execute the model, here you can see that we need to enable the gating pulses first. I will enable the gating pulses, and as soon as I will enable closed loop operation here. Maybe I can give a speed of 200 and I will enable the closed loop operation. No, I think we can have more speed so that we can see the motor spinning more. So I have given a reference speed of 1000. So when I gave a reference speed of 1000, I am able to get the actual speed here. Here you can see that the speed is slowly settling to this reference speed. And I will show you the connection setup here quickly because the motor is spinning now. And I think I would suggest every one of you to switch your screen to another video of mine. I'll just add my mobile to this Zoom meeting link so that I can show you the live video of the connection setup here. Let me just add my mobile quickly. Please hold on a minute. Yeah, I think I will stop sharing my screen, and I would suggest you to shift your screens to. I think I need to. How do I stop sharing? Well, Zoom meeting is quite new to me, so I'm not familiar like how to stop sharing so that you will be able to view my video, which I will show in my mobile right now. Can anybody in the audience just help me out in stopping the screen sharing? No, this is actually start video maybe. No, this is leave meeting. But yeah, I think somebody has taken control. Yeah, that's fine. Now I will quickly start a video from my mobile. I think you will need to switch your screens to Shivakumar mobile. You will be able to find it in the participants list. You can see the video which is being shown right now. Is my video available through my mobile? I think you need to change your what is it? Yeah, got it. Okay, so I hope my video is visible now. I can see it from my PC. So so this is the setup which we have right now. We have an RPS here. We are providing 30 volt, and this RPS is being connected to this inverter box. We are providing the DC supply to this inverter box here, and this converts the DC into AC, and these terminals are connected to the induction motor which we have right now. Here you can see the motor spinning. And coming to the most important part, the simulator setup. Here we have the simulator. So here we have those slots which was mentioned in that Simulink model. Here we have 1B where we connected all our all our gating pulses. Like this 1B slot is the slot where we sent all our gating pulses. So we are connecting the cable here, and this cable is being connected to this gating pulses terminal of the inverter. And also from the same cable we are sensing, we have some current sensors in this inverter. So here you can see some current sensors. So these current sensor signals are again being sent back to this 2A slot. This 2A slot is analog in. So this is where you got those current signals and we fed it to grid, but still that is not our area of concern now. Our area of concern is how did we send our gating pulse, and next one is how did we sense the speed of the motor. So the motor which we have right now, this is from motor solver. This motor solver's motor has an encoder attached to it. So we are connecting this encoder cable to this particular port of the inverter. What happens is these encoder pulses which is being connected here are converted to this DB9 cable, and this DB9 cable further converts it to this DB37, and it is being sent to this 1A slot. So in this 1A slot, we are getting our encoder signals, and these encoder signals are converted to speed, and that is the speed which is available in this in the MATLAB simulation which I showed you. That is the speed which is available right here. And now what I'll do is I'll try to change the reference speed, and I'll show you how the duty ratio of the pulses is changing. So I'm also measuring the pulses in DSO here. This is a Texas Instruments inverter actually. So there are some ports to connect the gating pulses. So we are measuring the gating pulses here. So currently for the speed for 1000 RPM speed, we have a duty ratio of around around 0.37, and yeah, here we go. Here you can see this is the gating pulses which is being generated. Here you can see the switching frequency information and the duty ratio information. Now I will slightly increase the speed to maybe 2000 RPM, and you will be able to see the change in speed here. Here you can see that the speed is slowly increasing, and it is settling to yeah, it is settling to 2000. Yeah, exactly. Now I will also show you the gating pulses generated in the DSO. Here you can see that the duty ratio has been increased in the previous case because we have increased the speed, but still the switching frequency of the pulses are constant. Since we gave just 19 kilohertz here, I can show you that also. we have given 19 kilohertz switching frequency here in the model. So the same switching frequency is being reflected here, and this duty ratio command is being generated by the simulator with the help of the control strategy which we implemented. Yeah, that is how. So, and I would also like to stress upon that this complete setup which we have here, some might confuse this setup to a hardware in loop setup, but in Opolarity we call this setup as a rapid control prototyping setup. Why? Because we have the plant outside and we have the control or the simulation which is happening in the simulator. So this is a rapid control prototyping based approach. So this is what I felt like showing here. The how do we make the simulation to interact with the external world? So we are trying to control the induction motor which we have here. We are sensing its speed command, and we are giving a reference speed command in this simulation. Depending on the reference speed and the actual speed, the gating pulses are being generated from this slot, and it is being connected to this inverter, and this inverter is converting this DC into AC, and it is controlling this motor successfully. This is what I felt like showing, and maybe I will stop the video for now, and I will be able to I will be more than happy to answer your questions. I think I was a bit fast in my presentation because of the time constraint, but still, if you have any confusion, I'm more than happy to answer you. Yeah, I think these are the things in which I felt like discussing. Maybe to summarize, I started with what is a real-time simulation exactly? How when do we need a real-time simulation, or why do we need it? What is its exact application? And after that, I told you how to configure the IO channels of the Opolarity 4510 simulator. And after that, I have shown a live demo on how are we controlling a real induction motor. Yeah, that's it. And if you have, maybe I could have explained even more, but still, due to the time constraint, I was not able to explain a lot of things. But still, I hope the overview of what is exactly a real-time simulation has been conveyed to the audience. And if you have any questions, please feel free to ask, and I will be more than happy to answer everyone. Yeah, I think from my mobile I have left now, so you will have just my laptop's link or laptop's account in your participants list now. Yeah.
Sir, am I audible?
Yeah, yeah, you are audible.
Yes, thank you, sir, for your valuable session. You explained how to dump the model, that is MATLAB Simulink model in Opolarity. Really, it is useful for us in our research area. So there is a question: which software package is used for automotive vehicle simulation?
Automotive vehicle simulation. Okay, all right. It depends on what kind of switching frequency in which you are trying to work, or what circuit you are implementing. What is the control strategy of the autonomous vehicle in which you are speaking about? You can go with normal. You can also try working with a normal without any software packages. You can just use our RT-Lab and MATLAB Simulink. But if you have any switching power converters inside that autonomous vehicle, for example, if it is being executed through a battery, if it is an electric vehicle based approach, and you have some power converters to be controlled in your simulation, then we would suggest EFPGA. If it is a normal autonomous vehicle based simulation, the RT lab and MATLAB will be more than enough. If you are trying to work with an electric vehicle based approach, then I would suggest the EFPGA sim software.
Okay, sir. Thank you, sir. Sir, kindly accept this e-memento on behalf of our IEEE workshop team as a token of our love for your presentation, sir. Thank you so much, sir.
Yeah. Thank you so much for the opportunity, and it was a pleasure for me to share my knowledge.
Thank you, sir.
On behalf of IEEE India Council and SRM Institute of Science and Technology, I cordially invite our chief guest, Dr. S. Hosman Tilagar, Director Academics, Anna University. In spite of his busy schedule, he has felicitated this event and gracing this occasion. Thank you, sir. And I extend my welcome to IEEE India Council Education Activities Vice Chair, Dr. D. Devaraj, sir, to grace the occasion and plan for all the arrangements. I also extend my welcome to our speaker, Mr. Vasant Kumar, to grace the occasion. I extend my welcome to all the sincere and patient participants, both online and offline mode. I sincerely welcome the volunteers of IEEE India Council and volunteers of SRM Institute of Science and Technology. Without your support, this event would not have made possible. And in this occasion, I also express my gratitude to all the speakers who have accepted our invitation to provide the session both in online as well as in physical mode. So we once again welcome you all to this valedictory session. Thank you.
Thank you, ma'am. For the past 2 days, it was like a flow of wisdom. We had many people, many experts from different expertise, felicitating their, sharing their knowledge with us. I call upon Dr. Sangeeta to give a detailed report on this today's section.
Bringing to another person here. So I think you have got a wonderful session for the past 2 days. This is for the information of the guests. This is an IEEE India Council funded capacity building workshop for cyber systems. We have planned a session such that on day 1 we have all the three. On day 1, we have planned the session so that all the speakers have come in physical mode and presented the ideas and understanding of cyber physical systems, simulation of CPUs using MATLAB by Dr. Dev from MathWorks, and communication technologies for CPUs, sensors and actuators for CPUs, and hands-on session on Arduino and Raspberry Pi design. Through their presentation, they have explained. On day 2, all the sessions were held in online mode, where we have a lot of industry experts sharing their real-time problems and their solutions offered by their corporates. So we have online session from EBTR, CSAR Pilani, and we have Dynafusion and OpenRT who have presented their works in hardware, in the loop simulation, etc. So totally there are 342 registrations initially, and when on the day of workshop we had 105 participants connected in online and 57 participants have physically visited the campus. So this is all about the short report on the capacity building workshop on cyber physical systems, simulations and model.
Thank you, ma'am, for giving us a brief report on this workshop. I hope this event has created a lot of memories and it has definitely impacted some wisdom